Well, let's get this second day of our electric vehicle workshop started. Welcome to all the participants. I see the participant numbers slowly creeping up. It's wonderful. We had a great session yesterday on charging behavior and the policy environment. And I'm sure most of you know me, but my name is Erin Whitney. I am a research professor at the Alaska Center for Energy and Power at the University of Alaska Fairbanks. We are co-hosting this workshop with the U.S. Arctic Research Commission, and I am emceeing today's sessions with Tim Leach, who will be joining us a little bit later this morning. While we're waiting for folks to join us, there were some questions yesterday about why or how I was broadcasting from my vehicle. So I wish this were my vehicle. If I didn't have an 8-year-old and a 9-year-old kiddo, I would have a nice clean vehicle like this. But while we're waiting, can anyone guess what type of vehicle I'm virtually sitting in? And your hint is that it is an electric vehicle. And you can write your responses in the chat box. All right. So while you're doing that, I will go over oh, someone already got it right. Model 3. You must be Tesla owners. Wonderful. Yes, I'm sitting in a Model 3 Tesla virtually. Again, my own vehicles are not quite this clean and sleek looking. Okay, so today we have 2 sessions. One is on operations and performance of EVs with an emphasis on cold weather performance, and the other is on grid impacts. The format will be the same as yesterday, where we have panelists, followed by a discussion, followed by questions. I want to remind everyone to put their questions into the Q&A box. There should be a place for you to click on that on your Zoom screen. I think we did a really good job yesterday of answering people's questions, either live or in writing, and we'll try to continue that today. If you are joining us new today and were not with us yesterday, please introduce yourself in the chat box. Again, if you were here with us yesterday, you don't have to introduce yourself, but if you want to, you can too. We're really happy to have everybody here. Again, you are muted if you are an attendee, and your video is off, so you don't have to worry about looking scary for us. And again, the webinar is recorded. We will be posting the webinar on the website along with all the presentations after the workshop, so please look for those. And then also, when and if you do log off the webinar today, a survey will pop up. So it's not a link on the agenda or anything, but it will just come up as part of the Zoom session. We encourage and ask you to please fill that out to help us do an even better job next time. We've already gotten some good ideas from yesterday's feedback and are appreciative of all of the suggestions. So without further ado, I would like to turn this over to Dave Messier from the Tanana Chiefs Conference, who will be moderating our operations and performance panel. Thank you.
Awesome. Thanks so much, Erin. I hope everybody can hear me well. So my name is Dave Messier. I work with Tanana Chiefs Conference, which is the intertribal consortia for the interior of Alaska, and I'm going to be moderating today's panel on operations and performance. Hopefully I don't swear too much, and hopefully Tim or Carolyn don't cut me off because I say something inappropriate. We've got 3 excellent presenters today. Michelle Wilber is a research engineer. She'll be going first with the Alaska Center for Energy and Power. She is a research engineer based in Anchorage, but she works for ASEP out of Fairbanks. She's got a BS in astronomy from Caltech and an MS in mechanical engineering from UAA. She's been involved with projects ranging from solar resource characterization to battery sizing for Alaska diesel microgrids. She is happy to be doing work that she hopes will continue to make Alaska a great place to live for her family and all Alaskans, and prefers biking over driving. Following that, we're going to have Nancy Brown and Jim Kaywood from the Duluth Transit Authority. Those guys have a wealth of experience transitioning some of their fleet over to electric vehicles, and a great deal of experience on the practical side of operating hybrid diesel battery buses in cold temperatures, which is something that I'm really interested to learn more about today. Nancy is she's studied the hydrogen bus program in Iceland and advocates for sustainability in public transit. And she strives for practical, sustainable solutions for the good of the natural world and its inhabitants. Finally, Megan Hoye is the Director of Business Development and Policy at ZEF Energy, an electric vehicle smart charging company based out of the Twin Cities, Minnesota. Megan oversees the development of business relations, marketing, and policy tracking engagement. Her work sets the strategic direction for customer offerings and helps educate stakeholders about the value of EV smart charging. She came over to ZEF from the Center for Energy and Environment in Minneapolis, where she managed special energy innovation projects and pilots for communities, utilities, and businesses, and worked on EV and energy code issues at the state, city, and state levels. So we are going to have those three presenters. A reminder that the participants are muted. As you guys have questions, please ask them in the chat window, and we will get to them afterwards. I'll be kind of aggregating a list of them, and we will go over them after all the presenters are done. So Michelle, I will turn it over to you and allow you to start your presentation.
Great, thank you so much, Dave. So let me get my screen shared here. Oh yeah, first I have to pop up the presentation, 1 second. So while I'm getting that going, I will say that I took a page from Aaron's book here and changed my background to be inside of a car, although I'm facing the wrong way, because this is a picture I took while we were driving down the street in Nome a couple marches ago. So that gives you an idea of our Alaska weather that we deal with, if you don't already have that idea, if you're from somewhere else. And this is not an electric vehicle, this is a large truck. So let's see, I should be there. All right, here we go. All right, so everybody can see my slides, right? It's the question everybody asks to start.
Yes, great.
However, it did not start from the beginning. You're gonna get a preview going backwards as I get to the beginning, sorry. So this is one of our moderators from yesterday, Sean Scaling from Chugach Electric in the Chugach Bolt Watson. So today we'll be talking about cold, and on another beautiful Alaska snowy winter day in Anchorage. So we'll be talking about cold weather impacts on electric vehicles today. And this is mostly from the literature. You know, we're really hoping to get a research program going at ASEP, and I'll talk a little bit about some of the things we'd like to contribute there. But I do have one contribution that I'm really excited to share. We've been working with a group of students on doing an EV zone map. So we'll get to that shortly. As you know, I work as a research engineer for the Alaska Center for Energy and Power, and electric vehicles really fit really well into our mission of fostering development of practical, innovative, cost-effective energy solutions for Alaska and beyond. And especially there's some really interesting questions around the interactions of electric vehicles with our remote diesel microgrids and how they can be used for demand response or perhaps in the future V2G sort of grid benefits. But we have been getting into this space more and more, and last November we sent out a survey to a number of people, got a bunch of responses, and one of the top things that came up was concern over low temperature effects on the performance of EVs. And I'm very happy to report that all of our anecdotal surveys of Alaskan EV drivers and a glance through the literature shows that generally the sort of traction and winter driving performance of EVs is superior. They're low center of gravity and heavy, and they seem to perform very well compared to light vehicles in snow and ice. But there are some, as we heard yesterday, some real performance considerations to take into account. And this figure for low temperature regimes of interest for electric vehicles, and this kind of informs the MAP project I'll bring up. there are some battery physics sides of things, and then the actual operational effects. So the car, of course, the battery is a large component of an electric vehicle, but it's not the only component. And there's a battery thermal management system, and the driver, the occupant, and keeping them warm, and all kinds of other things that go into how the car performs in colder temperatures. But if you just look at the battery physics, so the EVs on the road today have kind of a standard lithium ion battery. In general, there might be some small chemistry differences, but they're fairly similar. And those have some characteristic reactions to cold. And you might know, some of this, how batteries respond to cold, by taking your cell phone out in the middle of winter, and if it's below freezing and you're taking pictures of your kids ice skating or whatever, and you think you've got 70% battery, and as you hold that out in the cold, before you know it, the phone is dead, and maybe when you bring it back inside, it warms up enough to come back to life. But there's definitely some performance considerations there. So I'm not looking at the hot range at all. This figure starts at 21 degrees Celsius as the warm end, which is about 70 degrees Fahrenheit. Trained in physics, I like to use Celsius, but brainwashed like all Americans, I think of sensible temperatures in Fahrenheit, so I might go back and forth with using those today. But if you go warmer than that, there's some effects both on batteries and cars, of course, and some of those get pretty steep as you get hot with batteries. They definitely don't like to be hot, which is some of the consideration with fast charging. But I'm not going to go into that because we're talking about cold effects. So ideal is kind of around that 21 degrees Celsius for battery use, as well as for best range when you're driving an electric vehicle. When you get down below 10 degrees Celsius, there's a battery physics thing that goes on where if you are charging in cold temperatures, especially fast charging, the faster you charge, then you can get some lithium metal plating on the anode of the battery. And some of that can be permanent, causing degradation, and it can be catastrophic if you charge too fast, too cold. You can build these big dendrite crystals that could, in a worst case scenario, pierce the battery separator and cause shorts and fires and bad things you don't want to have happen. So you got to be careful. Your battery management system has to be careful about that possible lithium plating during fast charging at colder temperatures. So that can start to take effect, above zero, but really below 0 degrees Celsius, then that becomes a possible problem with just the battery physics that you have to manage. Then there's also higher internal resistance in the battery at colder temperatures below about 0 Celsius. And these temperature regimes are, it's a continuum, and also there's slightly different takes on this for different batteries, but as sort of a general guide. And you also then are having more viscous electrolyte, and so there's slower charging and discharging of batteries below 0 Celsius, below freezing, and again, that degradation during charging. And then below -20, so in all these cold regimes, batteries that aren't being used at all, that are just sitting there in storage, are quite happy, and often the colder the better. But as you get below -20 Celsius, there get to be some additional dangers that happen even if you're not using the battery, even if it's just sitting there, and you start to get into a freezing danger area. So how that relates to electric vehicles in practice is, they generally manage these things with a battery management system, including a thermal management system. So they can, just like if you've got a desktop computer, my son's a gamer, so he actually moved from an air-cooled to a liquid-cooled system for his computer. So those same kind of temperature management regimes can heat your battery instead of cooling it, and they generally do both in electric vehicles. So it could be air-cooled, air-heated, or liquid-heated, and there's a range of solutions depending on the vehicle. But in the 21 degrees Celsius range, you have good range, good driving distance per unit of energy in the battery. You maybe, if you like to turn on heat as it gets a little chillier, you might lose a little bit of range. As you get down towards 0 degrees Celsius, most people are going to be using something, and you can kind of preserve your range maybe by using a heated seat or heated steering wheel instead of turning on full-on blast cabin heat. But you'll definitely start to get lower range. And then you might have slower charging on fast charging to protect that battery from lithium plating. And then below 0, you're starting to have possible low power on startup where you don't have the same get up and go, and you'll get some warning in your car that that's happening until the battery can warm up. Again, that lower range and slower charging, and then that lower range can drop, you know, in Alaska, we definitely have evidence, anecdotal evidence of range dropping 50% or more of the nominal or the best range due to energy use, not just to warm the cabin, but also warming the battery at that point. And then there's an additional thing that keeps going, you know, below negative 20 degrees Celsius, those things in the block between negative 20 and 0 keep happening. But then there's an additional risk because of that freezing danger, that if you have a car just sitting there in an unheated space, unplugged, and the battery itself could be used, it can use up some of its energy to keep the battery conditioned. But if you end up with too low a battery, your battery runs out and you're not plugged in, then you're in the zone for risk of damage to your battery from freezing.
Michelle, there's some really good questions that just came in the Q&A that's kind of specific to your chart that you were just showing. Would you like me to read them out loud?
Well, it's up to the moderators. I know that I'll probably take my full 15 minutes. So if you want to go into questions now, I'm happy to.
No, let's keep going, Michelle.
Yeah, I can return to some things later. I'm pretty sure I can speak well to it. I have a problem. I thought if I kept it to like 4 meaty slides, I would keep this short, but in practice, I tend to go long. So I would love to get to the questions. I know I'm leaving a lot of specifics out, but we'll get to those in the end. So anyway, to kind of be able to visualize these temperature effects and how they might affect different parts of the globe, and you know, if somebody in Fairbanks is thinking, well, what does this mean for me? We came up with the idea that it would be great to visualize this. And we worked with some really great master's students at the University of Washington, and they're still in the middle of their data science capstone project. So this is a work in progress, and these are screenshots from a work in progress, but it's almost done, and we hope to get this up on the ASAP website. But the EV zone map that you see some screenshots of here, and it is the whole world. I've cut off the South because right now we don't care about them. And zoomed in on Alaska because that's, you know, my home. So, so what we're looking at here is an EV zone sort of rating that's somewhat comparable to a heating degree day map if you are an engineer. And it's based on the temperatures in a region, the daily average temperatures over the last 10 years from NASA data, and then looking at the literature on what those temperatures mean for range impact, and kind of averaging that over the whole time period, and then normalizing it so that it's somewhat technology neutral, so that hopefully as technology, you know, maybe batteries and the management systems change over time, that those zones can remain steady even if the range effects are maybe become different. And so I can explain this in more detail, maybe if there's questions on it, but I'll just let you look for a second, or hopefully you've had a chance to look for a second and compare that. You know, Alaska has a number of these broad zones. You know, obviously they're chunked. So Anchorage looks like it's almost the same color green as parts of Southeast Alaska, but you know, there's some definite variations within that, microclimates within the climate zone or whatever. But there's a number of zones in Alaska, and even though so this map, like I said, is fairly closely related to a heating degree day zone map. There's another map that I don't have a screenshot of yet that's in production, but I have some data from it on the next slide. And that's more like a USDA growing zone map, where you want to know what the minimum temperatures expected in your area might be, so that you know not to plant a peach tree in your backyard in Fairbanks, because it's going to die when it gets down that cold. So that's the maximum plug-in days map, and that's the number of days in a row that the temperatures were below negative, the maximum number of days in a row that temperatures were below negative 20 Celsius in the temperature record. So even though I would say that, you know, Fairbanks probably beats Kotzebue in that metric, as the interior of Alaska gets a little bit colder than most of coastal Alaska, even if you're further north. As you go north, you can see you generally are getting into these colder EV zones for the kind of the temperature regime over the entire year. And then you can see pretty clearly on this, and we'll see it again in the next one, that large parts of Alaska are in quite a bit more of a less favorable EV zone as far as range considerations over the whole year go, compared to the most populous parts of Scandinavia, Norway, where there's huge EV uptake. So this is the same map as before, but on the online version, this map will be interactive, and you can hover and get more data, or you can search and get more data. And, just looking at Fairbanks versus Oslo, it's in a different, I guess I'd say, harsher EV score region. The max plug-in days is 6 times as high. And this maximum range loss is probably needs fewer significant figures, but it's more specific to the data in the literature today for today's vehicles. And it's just using the best fit of the curve of range loss versus temperature for a bunch of different vehicles, and looking at what that maximum range loss on the coldest day in that 10-year period would be. And so you can see in Fairbanks it's about 70%, and in Oslo it's only about 57%. Now there's a huge caveat there, and this is where hopefully ASAP can come in. If I go back to the temperature curve, there's only data to negative 23 degrees Celsius. And we routinely get down to negative 40, which is handily the same in Fahrenheit and Celsius in parts of Alaska in the winter. The coldest temperature recorded in Fairbanks is about negative 50, negative 52 or so degrees Celsius. And the coldest temperature reported in Alaska is below negative 60 degrees Celsius. So there's quite a temperature regime that there is no data for. And there's an extrapolation of the curve. But I imagine that there might be really interesting things happening in that region, as maybe the heater for the battery management system is going full blast. And so maybe there's kind of a shallowing of the curve. And then at some point, it's not really keeping the battery warm enough, and maybe there's more interesting effects happening. So, so that's something we'd really like to look into. And then for the real world. So I would say don't necessarily let that scare you, let that inform you. This is a screenshot. I hope Kirk Martakis doesn't mind me using it here, but I think he sent it with his blessing. This is inside his boat that he owns in Cantwell, which gets plenty cold, and he keeps it parked outside but plugged in, and he doesn't really notice a huge amount of power draw from plugging in, although I do have some specific other data on that if people are interested. I probably don't have time to present it here. It generally does take some energy, of course, plugged in to keep your battery conditioned, and possibly as much or slightly more than an engine block heater, but in that kind of range, it seems. And at the screenshot, it's negative 27 degrees Fahrenheit outside, 74 degrees Fahrenheit inside the car. And I don't know what temperature it actually was while it was being driven, but since its last charge, it had used 51% of the battery for propulsion, 37% for the climate settings to keep the car at 74 degrees Fahrenheit, and 12% for battery conditioning. So that's, he and his son drive the car all over the place, are quite happy with it. It works great for them. It has excellent traction. All the Alaskan EV owners I talk to are quite happy. There are a couple of them that keep their cars parked in the winter in colder climates because of generally probably having older cars. And there's a couple of models that maybe their battery management isn't so set up to handle colder temperatures. But there are a lot of very happy northern EV drivers. Or at least there are a few, and we hope to continue to have more. So that's what I have today, and I'm happy to answer questions when we get to that session.
Excellent. Thank you so much, Michelle. I didn't even have to give you a warning. You nailed your timing. That's fantastic, and you set a great example for future presenters. So impressive. Well, that was great. And folks, just a reminder, if you guys could type your questions into the Q&A, and we will get into them after all of the presenters have finished, but we don't want you to lose your questions. So please do keep it handy and feel free to put it into the Q&A box. And so now we'll go to our next presenters. That's Nancy and Jim with the Duluth Transit Authority. And those guys have a decent amount of experience using electric buses for public transit. So there you go, Nancy and Jim.
Thank you very much, Dave. I'd like to introduce Jim Kaywood. He is our Director of Maintenance, and he is the highest seniority person at the DTA, and also the person that's dealt with our electric buses on a daily basis. So He's going to be the expert if you have questions on how the buses work. We're going to kind of talk about using electric vehicles in a commercial setting. And I have to say, it's kind of a treat to talk to a group that doesn't get rattled by us saying when it's 30 below outside. So, you know, usually we're talking to people in the southern part of the country. So this is kind of a treat for us. I'm going to share our screen. Hopefully you can see this. And let me get to this slide view. I'm just going to leave this because then I can see what's coming up next. So a little bit about how we came about getting our electric buses. Can you hear us, by the way, Dave? Can you hear us?
Yes, we can hear you fine.
Very good. So we originally started off with fast charge buses. We felt that at that time, the only buses that were available were fast charge buses. And we wanted to be a guinea pig. We willingly volunteered to be a guinea pig for the industry to see how these buses operated in cold weather.
Excuse me, I'm going to interject here. Are you trying to show your screen?
I am. I hit share screen. Is it not working?
No, we're just seeing you.
Oh, I'm sorry. Well, let me try this again.
You have to pick the actual.
There we go.
There we go.
There we
go.
All right. Thank you for letting me know that. So as I said, I'm going to push this down. We originally started with the fast charge. During the time that we were preparing for those, Proterra, who was the manufacturer that we partnered with, came out with a depot charged extended range battery bus. And after reviewing our system, they felt that the extended range bus was a better fit. So for the DTA, we purchased 7 all-electric 440 kW buses, and I'm going to go into that in a little bit. We also installed 8 50 kW chargers, and we put them into regular service in October. The reason that we went with the extended range buses was because on our system, many of our buses go out
4:15 a.m.
Yeah, and they're on the road until
1:30 a.m.
Okay.
So they just get a little rest overnight, and that's about it.
Right. So when we talk to people about looking at an electric vehicle, whether it's a car or a commercial vehicle, the most important piece of advice I can give you is to know how to use that, how you're going to use that vehicle. For us, we wanted the extended range so that it didn't have to stop every hour and recharge. That's what the fast charge buses did in our industry. A fast charge bus would work really well for people who run it like in a circle and can stop after every hour and recharge. Oftentimes those fast chargers are located on a road or in a place where the bus passes through on a regular basis anyway. The extended range buses, especially in cold weather, which you'll see in a moment here, we found that the range was highly impacted, just like your cars are, by the temperature outside. Fast charge buses have a place, the extended range, for example, maybe a school bus operation, if you're going out for a few hours in the morning and can recharge in the middle of the day and go out in the afternoon. Those also might be applicable in a very extreme cold environment. But the most important thing for you to understand is your environment, how you're going to use that bus, and what the impacts are of the weather on the range of that vehicle. So this is just a picture of our bus when it was at the manufacturer. This is the bus connected to the charger.
And this is in our building.
Yeah, this is in our building. So just as I said, what fits? That was our first lesson. You need to be able to make sure that when you use an electric vehicle, you need to know how it's going to work and what fits. You want your chargers to be located where the buses can access them easily. We found that there were zoning restrictions also for an overhead charger, for a fast charger, that kind of caused us to rethink our plans. Also, as we all know, when you charge has a big impact on cost. So if you're using your vehicles mostly, during the day and you can recharge them at night, that's a much more economical choice than just charging during the highest cost cycle from your provider. Here's the cold weather considerations that we talked about. We required a diesel-fired auxiliary heater. Because of the size of the tank, they're 12-gallon tanks, right?
12-gallon tank, correct.
So because of the size of that diesel heater, this vehicle does conform to the California Air Resources Board definition for a low emission vehicle. It does use diesel fuel, but it is clean diesel, and it qualifies for any RECs that may be available. Minnesota does not have credits, but other states may have a system for that. What we found was that originally the diesel heaters were set up as a backup, and Jim quickly decided that they needed to be primary based on the results that we saw from the range on the buses. We also discovered that the driver's cabin needed extra heat. We have a saying here that you can have a great bus, but if the drivers won't drive it, it's not going anywhere. So we embarked on a program to add driver safety and comfort in the cold weather. And that's all done, right?
Correct. And one of the other things we considered, you'll see in the notes there, we also added extra dash fans and vents at the driver's legs. As we all know, you open up the front doors, and if there's somebody, getting in and leaving, it just creates a vacuum into the vehicle, and their recovery time, is a little bit slower. We also, like probably in Alaska, we traverse different elevations. And for example, Duluth is a long city alongside of Lake Superior. And if we go up over the hill in the summertime, we can have temperature ranges within maybe 2 to 3 miles of 15 to 20 degrees. Northeast wind off the lake really affects everything, drives moisture in off the lake. And when that, occurs over the winter also. So we had to deal with, what we call our fogging effect. You want your operators to be able to see out the doors, see out the side windows. And so Proterra worked with us, added extra venting and louvered. They can shut them, the drivers can shut them off and pick and choose where they need the heat. But they've done a real good job for us addressing those issues, and I will say that.
Yeah. What Jim means is that it can be 40 degrees downtown and 65 degrees over the hill. It'll be 40 degrees and foggy downtown, and you can see the sun, and it's beautiful over the hill. So that creates a lot of problems for the drivers, and they have to have that ability to keep the windows clear on a moment's notice. Can you also talk a little bit about the regen that we enjoy?
Yes, and one of the primary reasons that they wanted to come to Duluth is we are a very hilly city. Most of our routes head out within the mall area, airport area, some of the surrounding communities around Duluth proper. And we run grades of, I think the steepest grade is 19%, and they all go up and down. So the energy used going up the hill, the buses, they are impressive traction-wise. Everybody's right. The weight of the bus, snow time, we run snow tires. We have to. They didn't think we needed them, but after our first snowfall, we proved them wrong. And then the reverse is, it was very amazing to us when they came in and the first vehicle that they just tested in Duluth, we recaptured a large amount of energy just in about a 3-block drive down the hill. And with the Proterra, our drivers have to learn to almost touch the accelerator pedal, because the regen will stop and park that bus.
Wow.
And so it'll recapture up to 10%. That one time we had 74 or 56%, and just down a short, maybe a 2-mile run, we recaptured 15% of that energy back. And that's, of course, good weather situations. We discovered when it is slippery out, traction control, and I'll just call it all of the smart capabilities of the bus. They've made adjustments. It's all in engineering, but they had to figure out how to take that slip effect. So the minute the bus lost traction, the regen kicks out, and it scared the drivers. they freewheeled at a brief moment, so I had to apply the brakes. So you get accustomed to not even having to touch the brake pedal or accelerator pedal to a point, and then all of a sudden it breaks free. And so they're working on that for us too, and they've got some good solutions.
Okay. Going back to our conversation about the effect of the cold weather on energy consumption, this chart is, we have a consultant that we work with, the Center for Transportation and Environment, and they track our electric bus usage and create reports for us. This is a report from March of 2020, and it kind of shows where, obviously, when the temperature is low, you're going to have more energy usage. And of course, when the temperature warms up, your energy usage, levels off. Unfortunately, it doesn't go all the way down. It just levels off a little bit. We did notice that we were having a little bit more energy usage during the real cold weather because the drivers were using the defrosters to help heat the cabin. So this is just based on a short test with the past winter. We intend to go ahead and track the performance of the buses again this year in the cold weather, because now we've added those extra heaters behind the driver's seat and the other things to help the driver stay comfortable. And hopefully we'll see less energy usage this winter because that diesel fired heater is really helping them with that additional convector behind the driver's seat. If you're really interested in taking a deep dive into the analysis of the changes in the temperature versus the energy usage, CTE, in conjunction with some of their partners, did a very detailed investigation. And this is the report. I'd be happy to send a link, or you can go on the CTE website or email Allison Smith, and they would be happy to direct you how to find that. But it's a very good scholarly article on the impacts for electric buses. If you're planning to buy an electric vehicle, whether it's a bus or some other commercial vehicle, we talk a lot about how much planning needs to go in for that. You need to at least plan ahead for a year for infrastructure. We suggest that you do hire somebody that's familiar with EVs to do the design for you and be prepared for cost overruns. One of the things that we did was when we built our system, even though we only bought 7 buses, we have capacity for 20. And the reason was it didn't cost any more to build in that larger capacity. We had to have a minimum size requirement for the equipment that we installed, and it didn't cost any extra to have that ability to expand it in the future. So the only thing we would have to do is run a little bit of conduit and install some more chargers if we wanted to expand our system. The other thing that we learned when we were doing this was that as we were doing it, innovations were coming left and right, particularly on the charging side, and it's still happening. We're still seeing a lot of new ideas and new technology coming on board. We're also working with our telematics vendor to develop a smart charging app for our building, and I'll show you why in just a second here. This picture, besides demonstrating why I'm not a professional photographer, is the junction box and all of the infrastructure that we put in for the new buses. This is dedicated to just the chargers so that we can track the energy usage. Each charger has its own meter, so we can go right down to the micro level in tracking the performance of these. Oops, I'm sorry. We also installed a 250,000 kW backup diesel, or is it diesel or?
It's a diesel generator,
Yeah.
250 kW.
KW,
Yeah.
yes, backup diesel generator. And what we know is that if our power goes out, because we're a vital service, we have to be able to put those buses out on the street. There, it's 10% of our fleet, and we needed to have that capacity to keep the buses charged. However, 250 kW is not enough to charge all of the buses at the same time if all buses were empty. And so what our consultant is working on is a smart charging system to be able to direct the power that the diesel heater provides to whatever bus Jim designates that needs to go. And that's some of the things that we talk about. You know, how are you gonna run these buses? Are the ones in the front going to be charged first? Are you going to charge up the buses with the lowest charge, state of charge when it comes into the, are you going to charge up the bus that has the longest run? Those are decisions that Jim's department has to make if we don't have native power, which can charge all 7 at the same time. This does not have the ability to do that. So you have to be able to consider those items when you're planning for your infrastructure. One of the other lessons we learned was to engage with your partners. Our utility company was a huge partner for us, and they actually passed new rates for the DTA so that we would enjoy a less demand charges when we were charging all of the buses. They can get pretty expensive at times. We also tried to have our center, CTE did some data for us because we do get a lot of questions, and there's a lot of people who are very interested in how these buses operate. So we do have a little chart kind of showing, okay, what's been the benefit. Now understand that this is only a short time that these buses have been out on the street. As we keep them going over the next couple of years, you'll see these numbers change significantly. But what I like about this is that they did take into account the emissions from the diesel heater. So there is some, allowance for that there is still some emissions, but it's not, it's not compared to what it's saving. It definitely shows a benefit. This is going back to what we talked about before about preparing for an EV vehicle. You need to have new procedures. In our case, do we want the drivers connecting them or the technicians? Jim is always monitoring the state of charge and looking at the weather to decide if they're going to go on this route or that route. They had to change how they tow. You actually had to conduct a training for emergency personnel. And that's something that a lot of people forget about, no matter what kind of vehicle you're operating. A lot of people forget about, letting your first responders know that when they walk in the building, there might be some stuff in there they hadn't seen before. So make a note to yourself to make sure that you include them in your process. We distributed the risk. We have an extra charger in case one of the chargers fails, which we have had that, happen to us. We do have extra spares in our fleet. We also, this is the part where, we haven't decided yet if we're going to have to buy a charger for the maintenance shop, but that's an area where those portable chargers are improving rapidly. You're going to see a lot of new innovations in that field. And then lastly, like you're doing here, stay informed. There's so much happening, and we really like sharing what we know and watching and seeing what other people are learning and can share as well. So, if you have any questions, feel free to contact us. This is our contact information, and Dave has it as well. So thank you for giving us this time today.
Awesome. Nancy and Jim, thank you guys so much. I think that it's so important to learn from folks who are actually doing it. And you guys both look like we were fortunate enough to be able to interrupt your work days, and we really appreciate you guys donating your time and sharing the information and the lessons that you've learned. So thank you guys. That was incredibly informative. Okay, so now we're going to go over to Megan Hoye. Again, Megan is with Zeph Energy, and I will hand it over to her.
Welcome everyone. Rounding out the 3 presentations, great information so far. I have a lot to cover, so I'm not going to waste much time. I'll just let you know that I'm joining everyone from Minneapolis. A lot been going on here, but cold climate sisters, if you will, and we'll be talking about kind of cold climate elements throughout the presentation, little threads. But I'm just going to give you a kind of introduction on who we are and why we have something worth sharing, a primer on electric vehicle charging. We'll talk a little bit about the value of smart charging, give you a case study, and then talk about some challenges overall. So again, my name is Megan Hoye, and I'm the Director of Business Development and Policy. let's get going here. Okay, so ZEF Energy, that's Zero Emissions Future. That's what the ZEF stands for. That is our mission to reduce the emissions from vehicles down to zero, but we are for profit. And we're an electric vehicle charging company, and all we do is smart charging. When I talk about smart charging, I like to kind of divvy that up into a couple different buckets to describe what we do compared to others that are in the industry. We actually design and manufacture chargers. We design, develop, and operate a smart charging platform or software or network. And then we offer services both on the site development side as well as ongoing operational services and support. And we can answer questions about that as we go. Oops, there we go. Some things that I just want to point out that are a little bit unique about us is that we make our products in the US. We actually manufacture in Minnesota, Wisconsin, and California. You know, relatively unique to us is that we take an owner's perspective because we are one and we have been one for, we've been a company for 7.5 years, and we've been owning and operating for almost 5 of those years. And in a world where the oldest electric vehicle charging companies are 9 years, we're a young elder. And this experience of owning and operating really puts us in touch with, you know, some of the challenges and the realities of owning and operating charging equipment. And we bake those insights and lessons learned into our hardware design, our software design, and definitely the services that we provide. Our CEO is a software engineer, and we really have a technical team and kind of really bring that to how we work with customers. So, you know, I think throughout the conversation, I wanted to be able to focus on a few things that are on this slide, so I'll call those out. But our value and our experience, what we focus on in a company, as a company, really kind of boils down to 3 things. Beneficial electrification. How do we get the most out of the resources we have today on the electric grid? And future clean energy resources. Number 2, mission critical operations and reliability. And that really speaks to, yeah, utilities, but to fleets, and that they need to be up and running, and how we can support that and how we do support that. And then flexible technology integration with our software and how it integrates with other business systems and operational systems. So you can see on the right here that we actually work across, these are the 6 main use cases and customer segments that we work with, and have custom, you know, user-centric packages that we've built out for these use cases. So utility programs, commercial and residential, but also transit bus, school bus, light duty fleets, public charging, and multifamily. So just kind of something to keep in mind in the background. And then I've collaborated with many utilities across the country, from California to Indiana to parts of the Southeast. We work a lot with cities and states as well. And then we do operate 80% of the DC fast charging network in Minnesota, Wisconsin, and North Dakota, with many locations. So just to give you a sense of some of our experience. So, all right, I'm holding myself to a tight timeline here. As I said, I have a lot to cover, but I'm gonna start off with a bit of an EV charging primer. Hopefully that's useful. So batteries need DC power, like any other battery. This is how EV vehicles and EV batteries work. So they plug into AC power. Plugs go into AC power. It's converted to DC. Then the DC power is pushed into the battery, controlling the rate of the push, power push, for the safety of the battery. We'll speak about level 1 for just a brief moment on the next slide, but level 2 chargers, they pass AC through the cord, AC power, and that acts as a ground fault interrupter. And then you can see here that there's an actual onboard charger on the vehicle that converts the AC power to DC. All right, so that's a level 2 situation. And then on the fast charging side of things, the fast charger itself converts the power from AC to DC. And then that allows the vehicle to bypass the charger that's on board because it's already converted, and the power goes directly into the battery. So a little background there. And, so what does that mean as far as the impacts of drivers and operations and time, how we use our time? So kind of like a nice cheat sheet here is level 1, level 2, and level 3. And level 1, 2, and 3 really are standards that define the output of power through these different echelons. And level 1 is really just a plug into the wall. So besides this chart, we're really not going to talk about that today because that does not allow for smart charging. But level 2 chargers would allow you 7 kW all the way up to 19.2 kW is what's available there. And so you get a full charge in about 4 hours, maybe 3 hours, and even lower time if you're going up to those higher power ranges. And then on the DC fast charging side, you get 50 all the way up to 450 and beyond on the fast charging side. And that's what those really high power chargers are what, Duluth Transit Authority and other bus companies and agencies are using and would need. So you can kind of see, and this is based on your average Tesla and Leaf models, or actually Chevy Bolt, were what was used to model the times here. And on the far right, I just want to point out that the maximum charger use in a 24-hour period here between, say, a level 1 and a level 2 and a level 3 is really important when you think about this from how we get a return on investment for a charger, and also just kind of how to use the benefits of smart charging for utilization from a utility perspective as well. How are we going to get the most benefit out of that new asset, the new charging station over a 24-hour period of time? So you have more charging opportunities when you can move chargers through faster, right? All right. So smart charging, why smart charging? There are chargers out there that are kind of colloquially named or coined dumb chargers. They do not have the hardware and then software behind it to really manage the charge. But here are the benefits. Let's talk about the capabilities of smart charging and some of the benefits to round out why smart charging. So, smart charging, the ability to control the speed of a charge at the local level, at the charger itself. So the capabilities of smart charging, and our smart charging platform is called ZEFnet. And there are a lot of similarities across platforms, but I'll speak specifically from what we do. But the smart charging allows data to be logging at revenue at the level of quality of data that is revenue grade. And that's inherent and embedded in the charger. So just being able to pull data, look at reports, download data for more raw data analysis, for longitudinal study and so forth. The smart charging software allows you to limit the kW draw either at a single charger or a group level. And we could spend a lot of time even just talking about this, but what that means is that you can have infinite amount of groups over, say, a grid or even a campus or whatever it is, that you can have multiple groups, and then they can be overlapping groups, so that they could be kind of held to different constraints at the same time and rectified through the charging software. And why is that important? Because that allows a charger or a utility, a host of a charger or a utility to reduce peak demand and also to avoid and manage demand charges. The feeder level load balancing, this is helping increase the benefits of existing infrastructure, at the feeder substation level, and up and down from there. but by having localized load control. So you don't have to aggregate it up much further, kind of at sub-transmission levels. The renewals dispatch, there's also opportunities to synchronize with renewables, whether they're on-site or off-site. We've actually recently finished a project with SMUD where they were using blockchain to do off-site pairing with renewables, local renewables. And then the software allows for taking advantage of time of use rates, whereas a dumb charger, you just plug in and you go. There's no way to understand that at certain times of day, there's going to be higher rates or lower rates and how to take advantage of those. Smart charging also enables a driver-facing functionality. This is really important, especially when you have multiple use cases at one charger. So if you're a public charger or public and light duty fleet and workplace all in one, you can manage those different use cases at the same time, and you can help increase utilization because of that at a certain charger. So in brief, what does that look like? What does that mean? What are the benefits? That reduces fueling costs, both on the KW side and the KWH side. Meaning, we'll talk about this a little bit later, but you can manage observed state of charge as well, and that helps you not have to charge more than is necessary at a given point in time. So KWH and KW. Increase grid benefits and place downward pressure on rates, utility rates long term. Maximizing uptime. This is vital for the fleets. And then the charging and telematics integration. This is a capability that we have. Not all companies have this capability, but that this, as Nancy and Jim were speaking to on the previous presentation about how to optimize operations and use that downtime at the bus depot to have lowest cost fueling and to happen as quickly as makes sense. Let's see here. This is just a brief snapshot because of so much to cover. I'm going to move past this, but this gives you just a brief look at what a page in the ZEFnet smart charging software looks like and some of the dashboards features you'd see. So just, pausing for a moment to talk a bit about cold climate on the EV charging side. Michelle really did a nice deep dive on how that affects the battery and the effects on the vehicle itself. And I'll just say that that's most important because really it's a matter of physics, as it is on the battery, but also on the charger. And for a charger, it really is going to either be in temperatures that allows it to operate or it won't. It's binary. So operating temperatures across the industry are actually quite uniform. As you can see on the right here, for a level 2 charger, you'd be looking at about -40 Fahrenheit up to 122 Fahrenheit, probably not an issue in Alaska, but -31 Fahrenheit on a DC fast charger side. And so, once you're getting into temperatures lower than that, the charger would just not be able to push a charge. However, if within the realm of those temperatures, the transfer of the charge would happen at the speed at which the battery allows, really. So the internal temperature of that battery in cold conditions, it may start to affect the battery take. As Michelle went into much deeper detail on this, but that can be starting to slow around 0 degrees Fahrenheit. But a bit of starting the charge, starting the vehicle up, either one of those, that can help warm the battery. That does help warm the battery, and within a few minutes, you'll start to be up to full efficiency of taking the charge. So I'm going to go through a case study here and try to be quick. There's a lot of good information here, but a utility in Minnesota called Wright-Hennepin Cooperative, they did a pilot and an analysis looking at I believe it was 11 customers that were on a pilot, a few commercial customers, mostly residential. And then they extrapolated from that. And generally, they were looking at this 18% growth rate over a 10-year period, so 2018 to 2028 is what they might anticipate over the next 10 years. Of course, this was done a year or two ago. So COVID impacts, I think we'll flatten that a little bit, to be determined, right, on how much. But that was kind of one of the assumptions that were baked in. And from that, you know, interestingly, they looked at what the unmanaged charging, so dumb charging, if smart charging was not happening, what would the impacts of that look like on their grid? And this is on a per member or per customer basis, this particular chart. So the difference between winter charging and summer charging. Winter charging, you're going to see up to 15 to 20% more demand, you know, total demand at a given point in time on a given day, usually in the evening, as you can see here. A little blip in the morning, maybe before heading out for work. And then in the summer, a bit smoother, but generally the same curve, but a distinct difference between the two seasons. And then when you put that on top of base load, you can see here that at those peak times of day, again, unmanaged, that you'd be looking at the EV load nearly doubling the base load, and what that kind of impact would have when they scale that up to total grid impacts, system-wide impacts, especially at an 18% growth rate or over a 10-year period. So system impacts, they kind of extrapolated that and looked at that at a system-wide level. Obviously peaks increase and peak times are extended. So some significant impacts that they saw here. And in summary, you know, yes, they are a small footprint utility, kind of an ex-urban, suburban and semi-rural utility. But uncontrolled charging resulted in a 49-year return on investment, extraordinarily long. The return on investment for smart charging was just a few years. I believe it was 8 years. But in comparison to 49 years of a 49-year payback, the writing was on the wall for them, and it pays to invest in smart charging upfront. And that means rebates for smart chargers and really helping facilitate smart charging, but also overnight charging programs, time of use pricing, some variations on time of use pricing. So other different options for customers that they were looking at simultaneously and to be layered on top of one another. All of this would also help the customers save on electric fueling. So it was a win-win situation. So, you know, we were discussing ahead of the presentation, you know, it's not like everything in electric vehicle charging world is easy, and not that anyone has said that this is all puppies and rainbows, but there are a lot of opportunities for win-win. With that comes some challenges. And so managed charging in most utility circumstances does make economic sense really from day one. I have more anecdotes on that as well, but it's important for a utility to get hands-on experience and to learn from their own vantage point what makes sense, and learn how much there is, how much the value is, how much they value smart charging. Infrastructure upgrades can be very extensive. And magnified impacts, when you look at broader electrification, are another consideration. Demand charges, if you're kind of looking at, especially on the fast charging side, this really is fast charging specific, this particular bullet point, but it really is a barrier to transit charging as well as corridor fast charging. The time for using a fast charger is usually applied in a situation where charging is inelastic. You pull up at a fast charger when you're moving along a corridor, you need to charge relatively quickly, or you're a bus coming in and you need to charge soon because you need to leave again also. So this will really hinder the ability to help increase the utilization of those chargers. People won't want to use them if they're moving along a corridor. It'll be too expensive. And then the cost of the demand charge is prohibitive for owners. That cost of electricity, will help, unfortunately, will prevent more installations and the proliferation of EV charging infrastructure access. I think lastly, I just want to point out that the ownership model of chargers, especially on the public and fast charging side, is not clear. You know, there are gaps here. This is something that we had figured out before, right? Gas stations, convenience stores, that was their role. But that is not, there's not a clear taker on that today. So there are really opportunities for cities, I would underscore cities, but also large institutions, convenience retailers, and utilities, and even certain types of developers to take on that role. And I think that that's something I encourage everyone to be, you know, actively thinking about, how to help fill that gap. And you know, we have offerings to help fill that gap as well. And lastly, if I'm not being kicked off, I'll take 30 more seconds here, and just to say that on that mission critical performance side of things, you know, some of the challenges of just serving reliable operations, that Zeph Energy is standing up some sort of best in the industry, not seen anywhere else, services to help operators with 365-day, 24/7 support. Same day replacement of level 2 chargers, 72-hour uptime guarantee for level 3 plug chargers, not the overhead pantograph chargers. That's an exception, but this is unheard of. And then just longer warranties as a standard practice, as well as integration of telematics with our software, and then pushing that out through our partner API so that it can be integrated into a building automation system and other systems that might be used by fleet managers or building managers. So I feel like I'm at my time, and I'll stop there.
Great. Awesome, Megan. Thank you so much. I would say you nailed it, and I feel really good about where we are with regards to the time. Thank you so much for the presentation. And now I'll ask the three presenters if you guys could turn your cameras on, and we will move forward with asking questions from the Q&A tab. And thank you everyone who was able to ask a question. I know that some of the questions that were posed were answered already, so we are going to go through the unanswered questions first. And if we've got time, looking at our schedule, we will go on to the answered questions. So I'm going to start right off the bat with a question asked by George Rowe to Nancy and Jim. What are your thoughts about battery swaps versus fast charging? Wondering if that might be relevant in the contingency classes where you're using diesel gen sets to power the chargers.
I'm not sure exactly if I understand the question.
Yeah, I guess let me rephrase it. I think if I can channel my inner George Rowe here. Did you guys look at all, I know that there's been some talk about doing battery change outs so that you could maybe have a faster swap as opposed to fast charging. Did you guys look at that at all when you were analyzing options?
We did. We did not buy the buses that we could switch to a fast charging system because there's extra weight to have that pantograph on the roof of the bus. We decided to go all in, committed to the long range, extended range battery. What we did do was we evaluated the different KW. They had a 330 model, a 440 KW model, and a 600 KW. At that time, we decided to go with the 440 because it felt like it was the best fit for a transit agency. The 660, I apologize, 660 was more for intercity buses traveling outside of the city. If we had to do it again, we might rethink that, but at the time, that's what was available. Going forward, the manufacturers, not just Proterra, but all of them are upgrading their technology for better drive systems, more efficient drive systems, more efficient operations. And so that battery, the size of the battery, how many batteries you have on the bus, you know, there's a trade-off from weight to KW, but with the more efficient drive systems, you might realize more without having to upsize the number of batteries.
And there's also leasing options becoming available. And, you know, we considered things like that too. Another thing we're considering, we're having work on our building, but we're looking to the future of maybe capturing and have battery storage, solar capability. We could place solar panels and there again have a system that could, you know, be used to in addition to powering up, but using renewable energy to combine the two. And they're looking into that also.
Awesome. Thanks, Jim. And another question, this was asked by George Rowe as well. What are your plans for end of life on the batteries?
We do have the warranty on the batteries when they reach 80% of battery health, which we monitor on a monthly basis. We have a warranty to replace them with new batteries. We own those batteries. So that's what Jim was talking about, that we may try to employ a solar recharging backup for backup power or for some other supplement to native power here in the building.
And we also found out that we have, we're just call it a Gillig family, and we have our diesels, we have our hybrid diesels also. And we've replaced a few battery packs on those. We had very good luck because of Duluth, the hills. We worked them, the flatlanders as we call it, seem to have more problems with those. But the battery packs are not completely dead. A lot of the hobby people, we understand that the Interdel system replaced our Panasonic batteries through the Gilligs, but people will buy those battery packs, dismantle them. And for example, there's a company that will recycle and they'll use them in like motorcycle applications or other smaller needs. So, you know, they do, I guess, dissect and resell each small cell in there, which is a good thing.
Yeah.
So.
Awesome. But overall, would you say it's fair to say that that question of end of life is really taken on by the manufacturer that you purchased the system from?
In our case, it was taken on by us. We decided that we wanted to own the batteries, but there is, as Jim said, there's an option. You can either own your batteries or you can lease them. And of course, the lease, the manufacturer takes them back and either repurposes them or does whatever they can for them. So it is an individual agency decision.
And also another thing that we did look at, and you know, like I said, the technology is rapidly developing, but we may not get the same battery pack back.
Yeah.
We will get the upgrade, new and improved. We may see more range out of things like that. So it's like buying a DeWalt drill, for example, or Milwaukee. You know, 2 days later after you buy it, you're all proud of it, and there's a new one on the shelf. And the next one, or 2 or 3 are being developed. So there's a lot to learn, certainly.
I appreciate the analogy because I've been looking at a 20 volt and it just makes my 18 look horrible.
I just bought some for gifts for my 2 sons and I'm jealous of it. The 20s are way better than the 18s. So.
Right on. Another question for DTA. This is from Mark Masteller, who sits on the utility board down in the Matanuska Valley. He is also a professor. Regarding regenerative energy capture, do drivers have some real-time data feedback as a gauge on the side of their dashboard to help them learn how to optimize the energy capture?
Yes, that's correct. And it's a very simple gauge. They just call it, the color shows if you're in the green, that's the sweet spot. And we're still in the phase of learning as we go. And what I want to tell everybody is, the technology is amazing, and growing pains we have as an agency, the changes in the weather, what we've been going through to try and increase range through, like I say, the diesel-fired heater. They were adamant about not putting that in, but we learned early on that, sorry, your buses are not going to be able to serve the public. Through telematics, the drivers will be able to gauge their performance. You'll be able to analyze all of that as you go down the road, but it's going to take a few years for everybody to get comfortable into being able to do that. So right now we see that data and it's very interesting, either the lead foot drivers or the people that feather it. The data recapturing, that's all through, you know, CTE. We see that. And like I said, it shows up, but we're still dipping our toes in the water, so to speak, and learning. And as Proterra is learning from us also.
Awesome. And it's great to have that kind of partnership. And then last question for DTA, and then we'll move on. Can you guys elaborate a little bit more about the zoning restrictions relative to chargers and their locations? And that question was from Mark Masteller as well.
Yeah, that's a good question. We originally had planned on putting a fast charge system with a head that drops down on a state aid road downtown where we have our transportation center. And the head didn't meet the clearance requirements from the state of Minnesota. So when we built the building, we had to have a provision to bring that charging system inside, and the building is built for it, but we decided when we went with the long range battery bus, we didn't need that fast charge infrastructure any longer. But what we did also found out was that one of the other places that we were planning on installing a fast charge system over a charger was at our University of Minnesota Duluth. And they have to have a higher capacity because they have labs and things where they use a lot of energy at times. And so it became a concern that if we were there charging and using a lot of energy at that moment that the lab needed it, that there might be some conflicts there from not only for demand charges, but just basically making sure that both our charger and the lab had sufficient energy to suit their needs. So there were zoning restrictions that we encountered, but there's also the availability, the raw power that's available that we had to take into consideration. And one of the things that I noted about spreading the risk, we have plans to put a charger on a different grid. Right now, all of our chargers are on one grid, even though it's on a dedicated circuit, and we can track them, and we have a backup generator. It is a best practice to put a charger on a different grid. So if your entire grid goes down, you have someplace else that you can bring those vehicles to, and it's critical for a fleet. You have to be able to have an alternate if the worst scenario happens.
Awesome. Thank you so much, Nancy and Jim. Those were great answers. Another question from Mark. This one, oh, maybe it's disappeared. I guess this one is from Josh Kraft. And I think this is more for Megan. Can you condition a charger in the same way you can condition a battery in order to mitigate cold weather effects?
You know, I think I understand the question, and I just don't think it matters. That it's, like I said, it's really binary. If the charger is operating in the conditions that I put on the screen, like -40 degrees Fahrenheit, it'll work. If it's outside of that temperature range, it possibly will not function. And so I don't think you can reach, it's possible that starts to be gray area. I mean, that's the testing, that's the manufacturer's kind of warranty. Outside of that zone, it's questionable. I don't think that you will get it to operate at lower conditions because by providing some conditioning ahead of time.
Great. And then I'm going to toss in a question on that. And this is based on my experience, I guess, living in the interior. And the numbers that you showed on your slide stated that the level 2 chargers will only work down to -40. I often see that rating on different pieces of equipment, and my take on it is generally that that's as cold as some of the testing labs get. And so I'm curious if that is a true restriction on the chargers, or if it's more kind of a soft number. The -31 degrees seems specific. The -40 seems like kind of a catch-all. So if you could elaborate on that a little bit, Megan, that'd be great.
Yeah, fair, good questions. I think that they're both equally fuzzy boundaries, if you will. They are both lab conditions. They are being tested against the same standards, using similar components. And so, like I said, it's not going to become 32 degrees below 0 Fahrenheit, and all of a sudden it's going to turn off. I think that is going to depend. I would say generally those numbers are a little conservative. I can say that we've seen chargers function outside of that realm on a day or two here and there in Minnesota, or you know, the arrowhead of Minnesota, or maybe northern parts of North Dakota and Montana, things like that. But I think that they're kind of equally, 40 is not rounded. It's just sort of the output, and 31 is the output of the tests as well.
Got it. And I always throw in there, and I would imagine other folks may drive older cars like myself. And if you live in Fairbanks, at least, I would almost guarantee you that not a single component in your vehicle, which is commonly outside at colder than -40, if you're up in the interior, is probably rated for -50, let's say. But we usually still have people on the streets at those cold temperatures. So I would just throw that out as some additional commentary. And thank you so much, Megan, for the answer. This question is from Jesse Keel. And again, to Megan, in your analysis, you showed your case study, I should say, you said your break-even period was 49 years versus 8 years. Jesse asked specifically what discount rate you applied, and were the utilities regulated returns, and what were the utilities regulated returns or corporate hurdle rates? I would actually just ask you in general to elaborate a little bit more on that break-even analysis, if you could.
Yeah, I'll say it's a great case study. We're actually working on publishing it in a short format or a white paper. But we actually did not conduct the analysis. That's what's extra excellent about it, is that it was conducted by the utility itself, right? So they can put their really practical spin and assumptions into all of that. It's a simple payback model. I know that. I do not know the discount rate. I will know that soon. I'll take a stab at 4%, but I cannot confirm yet. And then it's a cooperative, and in Minnesota, those utilities are not regulated by the PUC. Their rates are not regulated, and so they were looking at total infrastructure upgrades on the energy resource side, as well as the infrastructure side, distribution level side, and within that total cost and ROI.
Got it. Thank you. And so can you describe a little bit more in depth? So the ROI in general was based on the cost of the equipment, the charging equipment?
Right. So if you were to install an unmanaged or dumb charger, and then you were to scale that over 18% growth across their grid and their membership, their customer base, that what would the impacts of that do to their grid, and what kind of infrastructure upgrades would they need because of that scaled demand, mostly on the KW side. And then compare that to spending a little bit more upfront for a smart charger, which would be more expensive, but not a lot more expensive, somewhere in the realm of $200 to $500 more expensive, and more for higher power level 2 chargers, but a little bit more upfront, and then you manage that charge very nimbly going forward, and you mitigate all of those, not all the infrastructure upgrades, but many. And so what is the total cost of upgrades, even with smart charging? And then you compared the two. They compared the two.
Awesome. Thank you so much. And then a follow-up question from George Rowe in regards to the temperatures, Megan, that you cited for the usefulness or the operating ranges of the chargers. Are those equipment temperatures or outdoor ambient temperatures?
Fair question. Outdoor ambient temperatures. Yep.
Got it. Thank you so much.
Yep. This
question is from Andrea Toussaint. And for Megan again, is the ZEF network on green lights for both DCFC and L2?
So yeah, actually, if you are familiar with our company, 4 or 5 years ago, we were actually, our fast chargers were operating on Green Lots network. And right now, actually, by the end of July, well, they operate on our network now, ZEFnet, and that's allowed. DC fast chargers can integrate now with ZEFnet because we're compliant with OCPP, or the charging protocol, to allow that. So no longer with Green Lots. I mean, I think some of the old ones will be converting over, but nothing going forward.
Awesome. And then another follow-up question from Andrea, is ABB the DCFC you use the most?
We've worked with 8 different fast charging companies. We've actually had a lot of experience with those 8 companies, and we work with 3, and ABB, Tritium, and EVSE are the 3 that we work with as trusted partners.
Awesome. Thank you so much. And then this question is from Tony Slatenbarker, an engineer with Kaufman Engineers. I believe it's for Megan. Is the 72-hour uptime meaning it can operate continuously for 72 hours?
No, what that means is that from a fast charger standpoint, when a charger goes down, unfortunately, it is not uncommon that a fast charger can be down for extended periods of time. That might be more corridor related, but I've certainly definitely come across that in bus fleet operating situations as well. And so our guarantee is that it would only be down for a maximum of 72 hours. That if it is a plug style chargers, that means all of the fast chargers that are not pantograph, which are the kind that charge from above, that we would be getting that up and operating within 72 hours. So you could, you can plan accordingly for that reliability. That's what's meant by it.
Got it. Thank you. And I think that goes into what Nancy and Jim were saying in terms of operating a fleet and the responsibility that comes with that. And so I'm going to ask a question to Michelle, because there were, I believe you answered these questions, but just to add some broader dialogue, can you go through a little bit the EV friendliness level, or however it was phrased on one of your slides that discussed how appropriate a climate was for EV and what factors went into the numerical value that was given to those areas?
Yeah, absolutely. So the EV zone rating is really just based on range decrease seen at temperatures. So with that fitted and extended curve from the data on EV range versus temperature, the students took the average daily temperature from the record over the last 10 years. And for each of those days, they plugged that temperature into the fit and came out with a range decrease. And then that was averaged over the entire time period. So it's basically the average over a year, but kind of looking at a 10-year record. And then that was normalized so that it wouldn't present as just a range decrease number, because we, you know, as much as the literature is based on existing electric vehicles, we wanted to be a little more technology neutral with the map, at least with the number that we're giving out there on that. And so that normalization basically depended on the maximum range decrease number seen for any place on the globe and the minimum range decrease number seen on any place in the globe, and normalizing between that, setting that to 0 to 100%. And so it doesn't take into account, you know, I think George or somebody else brought this up in the comments, or no, this was, I can't remember who brought this up, but somebody brought up that does it take into account the fact that electric vehicles are you know, are more comfortable when you start them in the winter, especially if you can preheat them, but even if you don't, the cabin warms up sooner. You know, there are some comfort advantages in cold weather. There are some advantages to electric vehicles in cold weather, and we don't mean to unfairly advantage them by looking at the disadvantages, the range decrease in cold weather. But you'll see if you look at the full map, there are range decreases in hot climates as well from the hot weather. And so that's also on there. And so that's the main component of that part of the score.
Excellent. And so just to clarify, it didn't look at things like policy decisions by local utilities or governments. It was really based on temperature and range.
Temperature and range. It's to give you an idea of, if you buy an electric vehicle, what sort of range impacts are you going to see? And it doesn't, you know, you'd want to look at that maximum range decrease if you have to get to work and you're commuting a while and work is 50 miles away and you're looking at an EV with a smaller battery, you know, and you want to know how big, how much nominal range you need to buy to be able to absolutely get to work on the coldest day of the year. That range zone isn't necessarily going to tell you that, but it's going to tell you something about the energy use of your vehicle over the whole year for propulsion and battery conditioning and
excellent. Right on. Well, we are about to wrap up. I just have one more question, and it's going to be for Jim, because I'm from Fairbanks and I'm the moderator, so I get to have the last question, right? Jim, I was really impressed with the longevity, I guess, of the batteries you guys have out, and I may have written this down wrong, but I wrote that you guys have these buses get on the road at 4:30 and they're out till 1:30 a.m. That's two things. That's the electric buses that you guys are able to deploy between charges. Is that correct? And then secondly, does the 12-gallon diesel heater on those buses, does that last the full time, or can you describe that a little bit, how long that'll go for?
Okay, so the answer to your first question, that's our range of service. And we would never be able to meet those needs with an electric vehicle. So right now we use them in the morning, and we're learning, you know, our temperature ranges, what we can do at say, you know, 30 degrees, between 30 and 20 degrees. It's amazing, you know, how that's affected. So we can put them out on pieces of work, as I'll refer to them, maybe a 2 or 3 or a 4-hour piece of work, bring it back in with maybe, you know, 35, 40% of charge. We plug it back in, charge it up, and depending on that temperature, how fast the recovery is. On average, it's a 10% charge. So we would like to get that charged up, and we can use it for an afternoon piece of work. So what we're learning to do is in the warmer temperatures, we can put them out to like a 9-hour range. If it's 65 degrees, we've proven that. Bring it back in and plug it in, and then get it back out for a shorter piece of work in the afternoon. That's the game you play of, I'll call it chess in a sense. You have to calculate the work, where it's going to go. The telematics are huge. We watch this on our computer screen, and we have to calculate if it's on the far end of town, depending on the weather, it's going to be able to make it back in. That's comfortable for us, and we want to plug it in and reuse it. So that's one of the big things we look at.
Yeah, just to clarify, he means 10% battery recovery per hour.
Per hour, yes.
So
sorry.
if you, forgive me, if it comes back in at 10 a.m. in the morning, we have, you know, morning and afternoon peaks for our service, just like a bus company would for schools. So what he's got to balance is, okay, if it's 65 degrees outside, it won't take very long to recharge that bus and send it back out in the afternoon for a longer period of time. The 4:30 a.m. to 1 a.m., we do have diesel buses that can run that length of time. So they're not a one-for-one replacement for diesel buses yet. In the future they may be, but not yet.
And we do calculate in that we're comfortable for a lot of our afternoon work. If we put it back out, that it has maybe an 80% charge. We're comfortable with that. Then we can pick and monitor and say we can put it on this route, and we know that it's going to do, you know, 3 hours. So that's the learning curve. There's a lot of hands-on in monitoring this. And to go back to your other question, Eberspacher or Espar is the company that has our diesel-fired heater. They are very efficient. And for that 12-gallon tank, if we ran that at full on, we could run it for 24 hours.
Wow, awesome. Awesome. All right. Well, thank you guys so much, and really appreciate all the detailed answers and all of the talent that the folks at ACEP were able to bring together. I think a lot of great questions got answered, and the presentations will go out and they'll be on the ACEP website, and I believe there'll be contact information if folks that are participants have additional questions. But thank you to all of the folks that took time out of their busy day to present on this. I think it was hugely important to folks around the state. As I'm looking at the attendees, there are people from Juneau down to Anchorage, up in Fairbanks, so all over, and just really appreciate everyone's time exploring this topic. And so I will hand it over to Tim.
Thank you so much, Dave. And Tim Leach here, jumping in as MC to help out Aaron Whitney. And Aaron, thank you very much for MCing this morning, as I had some other needs to attend to. That panel was fantastic. So thank you again so much for all the presentations from Michelle to Nancy and Jim and Megan. Really valuable content there, echoing just, Dave, what you said a moment ago. I would ask for the presenters to stay on a moment more. Our wizard behind the curtain is going to keep this panel live to give the panelists the option to answer some of those questions that are up in that Q&A box. And that's valuable both to us at ACEP and the U.S. Arctic Research Commission, but also for the folks who are out there who are attendees, just to see if we can really thoroughly answer these. I think there's one more question that hasn't necessarily been addressed. So if you guys can take a couple quick minutes to do that. For everyone else, we will have a short break now, just shy of 15 minutes. There will be a time clock that'll pop up on your screen here showing kind of the countdown. We will restart at 10:45 Alaska time, and that will be for our fourth and final session, which is going to be on grid impacts from electric vehicle uptake here and the charging that is required. I'm really looking forward to that final session, but again, thank you so much to this session here. Great information, and we'll talk to you soon. Welcome back, everyone. It is 10:45 a.m. Alaska time here, and I know we've got attendees from all sorts of different time zones, including various sectors in the lower 48 and a few different countries, including some of our next panel here, which we'll introduce shortly. We're going to be starting the grid impacts session momentarily, and our moderator for this session on grid impacts is Estey. She's the Senior Director for External Affairs and Innovation at the Matanuska Electric Association, which is the electric co-op through which I am a proud owner member, and very, very happy to know Estey for a number of years. She's been really working with the team over at Matanuska Electric Association to bring forward innovative results and innovative programs there. So I'm happy that she's going to be moderating the session here on grid impacts of electric vehicles and charging infrastructure. We have a really rich panel, I would say, for this discussion of grid impacts. The findings that we have here, the panelists that we have here represent really a broad array of roles. We have a couple of electric utility representatives from Koplin down in Cordova area, and Turk. Our neighbors to the southeast, if we're sitting here in Alaska, the southeast location that Graham is hailing from is from Green Mountain Power in Vermont. Again, we've got representatives from a few different roles here. The utilities that I was just describing have some interesting perspectives, both in terms of the vision that Clay will be sharing here shortly, and then also the experience at Green Mountain Power that Graham will be discussing. And then we have a couple of different perspectives here that are included. We've got Scott Lepold from Geotab, and Geotab is a telematics company that you'll hear about here shortly, but they really bring in a large data set about the use of electric vehicles and how those, especially the newer electric vehicles, are going to be changing some of the grid demands within our current infrastructure that we've got. Let's kick it off here. I believe in terms of the order, we are going to go with Scott. Is that correct?
Yes.
That's correct.
Yes.
Okay. So Scott, if you can join us here, and feel free to give a little bit more of an introduction than I just gave to you, since that was very brief, but go ahead and start your presentation.
So good morning, everyone, or afternoon, depending where you're logging in from. I'm Scott Lepold, part of the Geotab team, working with the Smart Charge platform division known as Fleet Karma. I'm a business development manager working with utilities across North America, some outside of North America, to develop and roll out or deploy different electric vehicle load management and load monitoring programs. So to get started, just a quick thanks though to ACEP and the U.S. Arctic Research Commission for allowing me to join this workshop and share some insights from a study that we recently published, which was called EV Growing Pains. And through this report and the presentation, I'll highlight how EVs have impacted the electrical grid and what these impacts mean and how they've changed over the past 5 years. But just before we get into the core content that I want to share with you today, just a little bit of context further around Fleet Karma and Geotab, you know, our experience in the EV space, why we or I am here speaking with you today. So Fleet Karma itself has 13 years of experience in EV products and programs, which include the Smart Charge platform. Within that platform, there's 3 solution offerings, which include the Smart Charge Profile, Smart Charge Rewards, and Smart Charge Manager. And that's really the core or underpinning way that we collected the data to produce and publish this report. Other noteworthy solutions within the Geotab landscape is EV suitability assessments for fleets. So enabling a fleet manager to understand where and what EV they could be placed in their fleet or a specific duty cycle that produces a positive ROI. And then also there's EV fleet tracking services as well as ICE vehicle fleet services. But because we're going to be focusing on the Smart Charge platform, just a few highlights around that the platform. So we've deployed 23 programs across North America, some outside North America, and we're expecting to launch another 10 this year. Now, these programs are in partnership with electric utility and for their residential programs and their EV customers. But collectively, when we pull some of this data, what we have collected over the past year is about 39 million miles of driving data, 1.5 million charging events, 13.5 gigawatt hours of charging energy across 40 different EV makes and models, which is pretty much the coverage of the North American market. And again, just to set the tone for the data set included in this report, because we're drawing from data of programs that we've deployed and launched, the data set really is between two scenarios. So we have the Smart Charge profile, which is really a pure EV data collection solution, allowing utilities to capture real-world data to evaluate the grid impacts and monitor and identify load management opportunities. So what does that current load at current consumption rates and patterns look like versus how does that compare if there's a household TOU rate? And then just identifying where the opportunities are and where there could be some risks and mitigation strategies might be needed to be put in place. Smart Charge Rewards. This is a customer-controlled load management solution designed to create smart load growth by shifting EV charging to a more desirable time period and rewarding those customers for this type of managed charging behavior. So how was the EV growing pain study conducted? Well, we collected vehicle side data, and we did this by using a connected car device that reads right from the vehicle. It's a, we call this a C2 device that clips in the OBD port of the participant's vehicle, and then collects that trip and driving data regardless of where that vehicle goes. And what that allows the utility to do is have a 360-degree view of how those EVs are used. And as a result, it provides an abundance of data points where and when EVs are charging, what kind of load they're putting on the grid, and that's what we're going to dive into further. So as part of this study, we split the sample population into two groups. So we had one sample with for 2019, which included 2019 and earlier makes and models of vehicles. Then we had another sample group that included 2014 and earlier makes and models. And then we adjusted this sample set to represent the actual market share, which I will touch on in a moment. But really, in the underlying theme that you'll see through here is the biggest differentiating factor is the long-range battery electric vehicles that, you know, back in 2014 just weren't really as dominant in the market, and of course battery technology has changed too. So we'll dive into that a little bit further. But the bottom line is we're evaluating the EV landscape from 2014 to 2019 and sharing some of those results. So looking a little bit closer at the data set, again, 3,900 vehicles were included in this study, which allowed us to collect 10 million charging slices, or another way to look at that would be 15-minute interval data points across 760,000 charging sessions. 2.3 million hours of charging data was collected, 8,500 megawatt hours of charging energy, 28.9 million miles of driving data, again, across 40 different makes and models. Now, the one thing I'll just note off the bat here is in terms of the miles collected for the driving data, and it's explained further in the report, and most of the remaining slides will be around the specific charging. But one thing I did want to highlight at this point was within the miles of driving data, we were finding that suburban regions drive on average 80% farther than their urban counterparts. And so when you're thinking about how to identify EV grid impacts, it's important to look at the different EV segments that make up the entire population as it can relate to coincidental charging, increased load, different behaviors. And it's really important to really understand that unique region that you're looking to monitor and manage. So just taking a quick look back to 2014, the Nissan Leaf on the left of the screen, #1 EV sold in 2014, 30,000 in sales, which was about 25% of the EV market share, 24 kilowatt hour battery, and 6.6 kilowatts of charging power. Fast forward to 2019, the Model 3, #1 EV sold, 160,000 in sales, nearly 50% of the market share. 75 kilowatt hour battery, so tripling that of looking back at the Leaf in 2014, and approaching double the charging power at 11.5 kW. So on a whole, looking at long-range BEVs, which now comprise of 70% of EV sales in the US, they're using more energy, they draw more power at substantially higher level when charging, and we're expecting this trend to continue to increase in the next 5 years. For example, Rivian, the R1T with a 180 kilowatt hour battery pack is expected to release later this year. So EV adoption trends matter when thinking about grid impacts. There's a redefined industry standard for battery capacity and range set by customers, and 4 of the 5 of today's top selling EVs weren't in production in 2014, and most consumers are expecting about a minimum of 200 plus miles of range. And so what you're seeing on this screen here is looking at the breakout between long-range BEVs, plug-in hybrids, and short-range BEVs from 2014 to 2019. So in 2014, only 14% of the market share were long-range battery electric vehicles, long-range defined as 50 kilowatt hour battery pack or larger. And then in 2019, huge difference in the past 5 years to 66%. And again, we expect this trend to continue where the percentage in market share EV sold will increase on the long range BEVs, and the short range and plug-in hybrids will continue to thin out. And so what this means is that it provides opportunity from an electric utility perspective as more electricity consumption, but it could also be problematic if you're not prepared, as there's going to be an increased load on the grid. So home charging trends, of course, matter to the impacts to the grid, and we're seeing changes there. So as a result of an increased battery capacities, they've really changed home EVSE preferences. Level 2 charging is more powerful and popular now than 5 years ago, and that's what we're seeing on this chart here. So in 2014, level 2 charging was at about 63.4%, and we've seen that increasing now to about 80%. It should also be noted that of the home charging, we're seeing only about 10% of the charging stations being networked, and therefore, if you're thinking about an active curtailment program, it could be challenging because it's a limited space of who could be eligible to participate. But there are ways to send signals and price signals to customers to engage all of those EV owners, and we'll touch on that in just a moment. And again, as customers are demanding this and are wanting faster charge times at their home, this is really the result again, comparing that Leaf to the Tesla and the charging demands and needs. So why are long-range battery electric vehicles game changers? Because they have more than double the driving range of their short-range counterparts. In some cases, 330 miles if you're looking at the Model S or the Model X. So they drive more miles per month, resulting in greater charging energy consumption. However, with that said, charging behavior is less predictable, as greater battery capacity means less frequent charging. So as these vehicles have more range, they aren't plugging in each day, and it's more sporadic and individualized based on someone's behavior. But by capturing that driving behavior, really helps characterize that load across these different landscapes, even when comparing, the same make and model of how they charge. So what you're seeing here is long-range BEVs having average driving distance of over 1,000, short range, a little bit under 800, and then plug-in hybrids with 900 and using about 40% of their miles driven on their gasoline side. So all things to consider and are important to know for how to monitor, manage, think about planning for infrastructure when looking at the different vehicle makes and models out there, but we're seeing the long-range BEVs really taking off. So in terms of charging sessions, the 2019 group consumed twice as much energy per charge session than the 2014 group. So we're seeing the 2019 group in blue here at about 18 kilowatt hours per charge session, which is basically double of the 2014 group at a little over 9 kilowatt hours. And again, direct result of EV technology advancements, specifically that battery or their batteries.
Scott, just a quick note. We've got about 3 more minutes for your presentation to wrap up.
Oh, all right, great. So looking, yeah, no problem. Looking at the average power per charging session, again, doubling between groups from 2014 to 2019. The 2019 group 9.74 versus the 2014 group of 4.54. So now we're going to take a look at the increased system level load per vehicle. And in this study, we're looking at the summer peak across North America. And in 2014, which is the gray line here, 0.41 kilowatts in 2014, and it more than doubled in 2019. One caveat I should say here is this data is from the load management programs where they're deploying smart charge rewards. So we are seeing a shift here, but the key takeaway is the difference in how much has changed just in 5 years. If this was an auto-managed program, you would expect to see that load here. So it does say and suggest that managed load using price signals can be an effective way to harness that EV load and move it to a more appropriate time. So looking at the street level now, we took 5 randomly selected EVs from each vehicle type for a single day. And when looking at the long range BEVs, we're seeing a peak of 7.34 kilowatts. So, thinking about when you might have multiple Teslas on the same street, what does that mean at that transformer level, especially when you layer on top of the household load? And it doubles and dwarfs the short range BEVs and the plug-in hybrids. So could pose significant risk if left unmanaged. So I'm just going to be a couple more slides left comparing customer controlled charging with untreated. What you're seeing in the dark blue here is that managed charging using, say, smart charge rewards, where you see a complete shift to overnight periods and flatlining out. When we look at household TOU rates, we see with the untreated group in the gray, there is a movement to that new time, but if this is overlaid onto the household load, you would see a secondary peak. And so it's a great opportunity to capture that load, shift it to the appropriate time. So just to wrap up, rapid shift to long-range BEVs. We're seeing, 14% market share 2014, 70% in 2019. They're driving further, more often, creating greater charging demands, and we're seeing that doubling as well. Increased at home level 2 charging, and of course they're charging at higher power levels. So from the utility standpoint, we feel that EVs have a large impact on the grid, require attention. The fastest growing segment are the long range BEVs, but they also provide the most manageable source of load to move. And if we peeled away some of the high level average data, we would actually see in specific programs that 1 kilowatt peak load that I mentioned earlier could be actually higher into the 1.6, which was coincidental with evening peak. So to wrap up, the ability to shift load using price signals in a scalable manner, engaging everybody regardless of the make model or the type of charging equipment they have. And then each region is really unique, and to make proper insights for infrastructure planning, load management, it's important to have that regional data set. So as I say with many of our customers and partners, you can't manage or plan what you don't measure. So I'll just leave it there. Looking forward to the discussion. Thank you very much. I hope you found this very insightful.
Thank you, Scott. I wish we could clap for you. We can maybe, but listen, thanks everybody for your patience. I was on and I could hear everybody, but couldn't hear me. So I may have to go to therapy about feeling invisible, but we're back on track. So thanks, Scott, for just stepping in and starting your presentation, and for Tim for moderating while I figured out my technical glitch. So that was a great intro. Scott had some good information there. I mean, we've got a great group of panelists here. It's a diverse audience that's listening. We'll do our best to facilitate discussion. And I think we're going to retread a lot of ground. I mean, when you look at grid impacts, there's things from charging behavior and policy and performance that really integrate into all of those. So we'll probably be retreading some of the things that folks talked about, and we'll get through questions as soon as we can. And I think as we're all looking at this, we all have different perspectives of what a grid is. Our Alaska grid looks different than, say, the lower 48 or globally. And then even within Alaska, our grids look different. And so I think this will be an interesting conversation because we do take a look at kind of the big to the little. I think we also all have different perspectives about what a grid's supposed to do and what grid impacts mean. From a utility perspective, I'm here thinking about frequency thresholds and power quality and infrastructure needs and things like that. We have a different lens. I mean, utilities, we're kind of looking at this as a grid as like a sacred beast almost, where it's a little unpredictable and erratic, but if we treat it right, it does well. And I think our members are seeing it as a tool now. And it's not good enough just for the beast to be well behaved. It needs to take on new functions. And so it's good for us to see that perspective and realize that it can be used as a platform. So I really appreciate you, Scott, starting down that path. And I look forward to conversation because I know there was a lot more depth in your presentation that we were able to get to. So I'm adjusting the schedule just a little, or the order a little bit, just to start with kind of more of the statewide and national perspectives and then narrow down to Alaska. So our next presenter is actually going to be Graham Turk. And he's a member of the Innovation Development Team at Green Mountain Power. And his work involves designing and executing innovative pilot projects in these areas, including electric vehicles, storage, and responsive demand. So Graham, I'm looking forward to your presentation. Take it away.
Well, hey, everybody. Thank you for tuning in. As Julie mentioned, my name is Graham. I work at an electric utility in Vermont, way on the other side of the country from you guys. And we are about 75% of our state. We've got 250,000 customers, and most of them are residential, about 200,000 and 50,000 commercial. And I'm going to talk today about a pilot program we ran with managed charging, and then just some general trends we see from the data we've gotten from that program. So real quick, load shaping 101. This is a principle that guides a lot of our programs, especially when we are managing flexible load like electric vehicles, like battery storage, and larger commercial loads that we're able to communicate, where our costs are driven by a handful of hours over the course of the year. It's really 13 single hours, which is the highest demand hour in each month. And then the highest hour for the entire New England region, which is one connected grid over the course of the year. And so when we look at how do we manage these resources, a lot of it is geared towards avoiding those peaks, because every kilowatt we can shave, every little increment of energy that we can knock off those peaks directly translates to savings for our customers. And so this is just a simplified example, but the bottom data is real. This is coming from our EV program, where the dark blue line is actual demand, the light blue line is the baseline. And in that instance, we were able to shave about 200 kilowatts off our peak, where almost every person in that program responded and opted into the event, which is why you see almost at zero the actual demand from the period of 5 to 9 p.m. Great. So in high level, this program offered unlimited off-peak charging for $30 a month. So as long as customers did not opt out of those peak events, they would pay $30 flat for as much charging as they wanted to do. They shared access with GMP to do those managed charging events. That was through the charger. We use ChargePoint and Flow smart chargers that we communicate with through a device management platform we use called Virtual Peaker. And then if a customer ever needed to opt out for whatever reason, they needed to charge their EV to get to run an errand at night, they were always able to do that, but they would pay a higher kilowatt hour charge during the event, which reflects that those high energy, high peak times are very costly for all of our customers, and they've already gotten the benefit of the $30 a month unlimited charging, so would pay a bit of a penalty if they weren't able to shift their use according to that event. A few more details on the pilot. On the left is an example of one of those peak events. So we notified customers anywhere between 5 to 10 times a month that, hey, peak event's going to be occurring between these hours. You don't have to do anything other than not opt out, and the charger will ramp down to 0 and then come back on automatically as soon as the event ends. This was really successful because most people just need their EVs charged by morning to commute to work. And so as long as that charge happened sometime between when they plugged in at home in the morning, it didn't matter so much when that occurred. So you have a lot of flexibility to avoid these high energy, high price times and charge in overnight hours when energy is much less expensive. A few examples of how we promoted this. We put a lot of information on our website. There were stories in local newspapers and got the word about the free charger, which if you purchased an EV, you'd get one of these for free. We still have this program, and that was a big draw so that customers only had to cover the installation and would get the charger for free and immediately be able to start saving. A little more on the technical side, so how we're actually doing this from a billing perspective, in case anyone's interested. We get data directly from the charger. That comes through our device management platform, and then we back out any charging that happened from the smart charger on the bill from the home's total consumption. So we're kind of reconstituting that added load from the charger and then adding it back at the special rate, which in this case was just $30 a month. And so that's before, so I spoiled it a little bit, but just an example of how effective it is when you do these events. These are back-to-back days, so roughly the same amount of vehicles in the program. One where we called an event, which ended up being the regional peak day for all of New England, that's the top, and then just the day before with very similar temperature and conditions on the bottom. And so you see a pretty drastic reduction during that event, and all of the demand that's occurring on the bottom picture between 5 to 8, that would have been on during our peak, increasing costs, which has an increasing rate pressure on customers. So just by shifting this use to later at night in one day, we were able to see some huge savings. Some outcomes quickly on the pilot. So one was that charging a flat $30 a month did lead to a lot more consumption than we expected. That wasn't necessarily a bad thing, but it was helpful to learn how to design new programs so that we baked in those assumptions up front and that customers were saving according to the amount of benefit they were providing to all of our customers. The low opt-out rate was really key. So recognizing that customers are okay with allowing their utility to shift the use of their charger if it's done in an easy and non-invasive way that they don't have to switch their behavior. They can just let it happen behind the scenes. And the program penciled as a net benefit of almost $30,000. So it was a really great outcome and got great learnings, but also direct cost savings for our customers. So here, just some more data directly on EVs. And this is part of the benefit of having access to these chargers and managing them is that we also get really clean data directly from the chargers. It's not the home's consumption. We don't have to disaggregate. It comes right from charger consumption. The top left, we see typically weekday. These are all uncontrolled days. And so you have a pretty similar profile for all weekdays, a little bit lower on Friday. The weekend is distinct, where there's less overall charging and a smoother ramp, I think, because fewer people are coming home right at the same time after their commute. The bottom right slide is just a kind of year-over-year comparison to show some of the effects of COVID, where because people were doing a lot less driving, you have overall lower charging, and also days start to look more like the weekend because the charging is spread out more throughout the day, as opposed to, like I said, everyone returning home at the same time. Seasonally, we also see variation. So January is about 40% higher total consumption than in August. And this is, for a number of factors. One is just battery chemistries and batteries performing a little bit better at higher temperatures, also cabin heat. And so more energy consumption overall, but not a huge amount. And I'd say too that as the EVs are getting more efficient in how they do cabin heating, I know Tesla and Nissan and maybe a few others have heat pumps as options for doing that. I think that these curves will close in how far apart they are, so you'll start seeing less variation seasonally in consumption. This is just another way to show what I did before, but I love rainbows, and so I had to include this one just to show just how consistent the weekly variation is. So the dark blue and the purple are Saturday and Sundays, and consistently week over week you're seeing lower consumption than weekdays. And then lastly, I know that there's a lot of concern about what happens when everyone gets an EV, and all of a sudden, do you have spikes in demand that the infrastructure isn't able to handle, and that you need to do all these replacements of transformers and breakers. So we ran a simulation where we assumed that we had 50% and then 100% penetration of EV charging, and no control at all. So customers just plugging in whenever they happen to get home. The results show that yes, we'll have to have a couple of, handful of device changeouts, but nothing like the apocalyptic scenario where all of a sudden the entire grid explodes because of all this added demand at the same time. I think part of that is just due to the natural variation you get across hours as people come home at different times and have different rated chargers. And then, if you overlay on top of this the ability to do the managed charging, then it's even less of an issue, because you could bring all the chargers back at different times so you don't have so much of a snapback, and implement different charging strategies so that you're avoiding the impact of load coming on at the same coincident hour. Lastly, this was part of our integrated resource plan. So we looked at different scenarios of EV adoption in Vermont and what it would add to our cumulative peak demand as a state, and then also consumption. We saw that in even to high growth scenarios, wasn't a crazy amount of added peak demand. I think this bottom here just gives a couple of those stats. And we've seen roughly consistent, backing out them in the last couple months where overall vehicle purchasing was pretty down. The medium growth scenario has been consistent with what we've seen in the last 3 years. So an added demand, on the order of a couple megawatts so far, and trending towards about 40 by 2028. And then on consumption, EVs, an average EV in Vermont consumes about 3,000 kilowatt hours in a year, which is significant, and for some homes could be almost as much as the rest of their household use. So it's a significant load addition, helps provide a rate reducing effect for other customers because you're spreading out consumption over the same fixed costs. And so we're big proponents, and obviously for not only the how it affects rates, but also emissions, where in Vermont, transportation is our number one source of emissions. It's about 45% of all of greenhouse gases. And with a grid as clean as ours, we have about a 90% carbon-free energy mix. EVs represent an even greater emission reduction than the national average. So a couple of takeaways. I'm happy to discuss any of these in the Q&As, but the EV charging management, they reduce peak-related costs, which benefits all customers. And we know we can do it in a non-invasive way that customers are okay with, because it's providing them with a benefit and they don't have to change much about their daily routine. They can let the technology do it for them. We use their data from our pilot directly to inform a new tariff that's currently under review at our PUC, which offers two different possibilities for a managed and more traditional time of use EV rate. And we're still continuing to provide a free level 2 charger with the purchase of every EV, which has been really critical to get customers onto these rates, to do this sort of charging management, and to take the decision out of their hands whether to purchase a smart charger that has these abilities, or to just plug into a wall. And I think there'll always be a place for level 1 charging, and for having a portable charger, especially on road trips or visiting friends who might not have EVs. But it's been really important for us to have access to that charger directly, so that we've been able to do some of these more sophisticated load management techniques and get the benefit of savings right away. That is it for me. Happy to answer questions at the end or in the chat, and I'll kick it back to you, Julie.
Great, thanks, Graham. Wow, you were efficient. Nice work. Yeah, it was fun to watch and learn a little bit more about how other utilities are being innovative around the country. So there were a few questions for you specifically on the Q&A. So if you want to handle those offline, that's great. Our next speaker is Clara Good. And Clara is an associate professor at the Department of Technology at the Arctic University of Norway. She's also part of the interdisciplinary Arctic Center for Sustainable Energy, where she's one of the team leaders for research area transportation. Her research interest is electric transportation combined with renewable energy systems, and she's got some really interesting perspectives to share. So Clara, I will let you take it from here.
Thank you for the invitation, and good evening from Tromsø. Yeah, it's been really interesting to listen to all the presentations. So I can just perhaps add some perspectives from the other side of the Atlantic, and some experiences from Norway where we've had quite a lot of uptake of electric vehicles in the last years. So I'm going to talk a bit about that, and I'm also going to talk briefly about a study that we have done on large-scale integration of electric vehicles and solar energy up in Tromsø. So we're located up in the north of Norway. I was just going to start with the electricity situation in Norway. So our grid is about 98% hydropower. So basically the electricity in Norway is renewable hydropower and a small fraction of wind power. So we have historically we've had high use of electricity for heating our houses, and in general a high use of electricity since it's been available and controllable, and also historically very, very cheap. So today around 50 or 60% of the energy we use in Norway is electricity. Kind of echoing the last speaker, transportation is one of the highest. Well, that's the reason that we have about 50% fossil energy use. So this is a projection for total electrification of Norway, and that we see that, of course, electrification of transport will require more electricity, but will significantly reduce the need for energy, since electric vehicles are so much more efficient. So today, transport accounts for 23% or so of the total energy, or a quarter of the energy demand, but about 40% of the emissions. So if we only look at personal vehicles, you can see that the energy demand will be more or less half if we can electrify our transport sector. Let's see. So I usually like to show this slide. This is the development of the EV market share in Norway. So since the beginning of, well, since 2010 or so, we have had a steady increase year by year in the market share of EVs. So this year we have reached 50%, or projected at least 50% market share of all new vehicles are battery electric, and plug-in hybrids account for another 20%. So this has led to 9.3% of the entire personal vehicle fleet being electric. If you also account for all the hybrids, that's another, it accounts to 70%. But there are large regional differences here. So up north, where we are situated, the share of the vehicle fleet is around maybe 1 to 3%. But in Oslo, in the capital region, the share is around 17-18% electric vehicles. So there are, of course, many reasons for that. We have heard about the development of long-range electric vehicles, and up here we have a lot of yeah, we have large distances and a less developed charging network than in the southern Norway. So I'm not expecting you to read all of this. I just wanted to add some background into how we got where we are with the number of electric vehicles. So this is a list of the incentives that the Norwegian government or governments have introduced in order to increase the number of the EVs. And the current ambition of the current government is that by 2025 there should be only electric vehicles, or there should be 100% market share in new personal vehicles for EVs. So by far the most important incentives have been these two, that if you buy an EV in Norway, you don't pay purchase or import tax, and you don't pay VAT on the purchase. And the result of this is that buying an electric vehicle or buying an ICE or a fossil vehicle, it's around the same price. Buying a car in Norway is expensive to start with, but with all of these incentives, it's more or less the same price for similar cars if you choose electric or ICE. And then you have a lot of savings from the charging instead of driving on fuels. So another important incentive, or something that has led to this development, is the program to finance a network of fast chargers throughout the country. So at this time, there are around 4,000 fast chargers throughout the country. And the objective is that there should be at least 2 multi-standard charging stations every 50 kilometers on all the main roads in Norway. And I put an arrow here up where we are located in Tromsø. So you can see that we haven't quite reached that goal up here and further north from where we are. So this is one of the reasons that the share of electric vehicles is kind of lagging behind up here. So I've been driving an EV myself for the past 4 years, and until maybe a couple of months ago, I haven't really been able to go further north from here because there hasn't been anywhere to charge. So this network of charging or fast chargers has been really important, I think, for the uptake of vehicles up here. But of course, as was discussed yesterday in other sessions, in other regions or in other regions of Norway, other incentives have of course been very important, like you don't pay toll on toll roads, or you can ride free on the ferry, and free municipal parking and access to commuter lanes and so on. So it's combined, all these combined perks has led to a large uptake in most of the country, at least. So the study that we have done at the university here is a study about large-scale or city-scale integration of solar energy combined with electric vehicles. So we asked what would happen if everyone in Tromsø bought an EV and installed solar power on their house. And we've done this study together with University of Uppsala in Sweden. So we have done the same study in Uppsala, which is a slightly larger city in the southern part of Sweden. So why would we look at EVs and solar energy then? Well, as I said, our grid is more or less fully renewable, but we find that solar energy is the most suitable energy source if you actually want to integrate your energy source into urban areas. So this has, of course, several advantages. One is that there is less conflicts over land use, but also that you get closer access as a customer or as an owner to your energy source, which has been important for a lot of EV owners, because experience from solar installers show that EV owners in Norway are more likely to install solar energy systems. So the people who install solar energy systems here are EV owners and their neighbors, according to installers. So I wanted to add this picture because this is one of the very few solar energy systems that we have up here in Tromsø so far. I think there are 5 in the city. So while we've had quite a boom in EV uptake, we're so far very much in the starting development on solar energy, and also the fact that solar and EV has kind of opposite influence on the power grid. So out in the weak grids or the end of the grid, we get an increase in voltage from the solar, and we get a decrease from the EV. So we wanted to see this. We wanted to look at the combination of these two. So I've been working. My background is not so much in EVs as in solar energy. So I think I cannot count the number of times that I've gotten this question: isn't it too dark and too cold up where you live to use solar energy? So people tend to forget that we have half the year we actually have a lot of sunshine, even though we have, as you do as well, half of the year quite a lot of darkness. So this is just a picture from our campus where we put up a solar cell system to actually measure what we can get out of it. So we have put up solar cells in different orientations to just get some facts on the table to be able to show what we actually get up here. And it turns out that what we measure is not very different from the southern parts of Norway or even the northern parts of Germany. So basing the calculation on what we measured, we came to the conclusion that around 20 square meters of solar panels, that would be enough to drive on renewable or on solar energy for all of the year, with the average driving distance of a Norwegian EV owner. And that's been a surprisingly small area to many people that I've talked to up here. So the study that we made, we calculated the suitable area that were available on buildings in Tromsø and in Uppsala. So we used a kind of rule of thumb approach, taking into account orientation of buildings, areas that are available if you disregard windows or architectural issues or other effects. So the area of buildings in general that are suitable and available for solar energy, we calculated in Tromsø and in Uppsala. And then we, with our partners in Uppsala University, made a simulated study of the charging behavior of electric vehicles. And this is based on measurements from Sweden and also a travel survey from Sweden. And based on this information, our partners in Uppsala, they have simulated what the charging would look like for scenarios ranging from 10% of the personal vehicle fleet up to 100% in both our cities. And we've done the same with the solar integration. So we've looked at what would happen if we installed solar energy on 10% of all the suitable area up to 100%. And of course, that's quite far from where we are now. As I mentioned, we have 5 small PV systems. So this is very much so far a theoretical study. So this shows what it would look like if you had 50% EV share up here and we'd install solar cells on 10% of the suitable area of our non-residential buildings. So we're just looking at one day. We have our partners identified 3 distinct charging behaviors from the measurements and from the simulation that we have charging at work and at public chargers, and we have a peak from charging at home. So we analyzed the solar fraction that we can get. How much of this charging can we cover by solar energy in our different scenarios? And we also looked at the load mesh. So we unsurprisingly see that with home charging, which is this peak here in the afternoon, this is not a very good fit with solar energy. The solar fraction that we got was around 40% or 42% in July and 11% in March. We looked at the month of July and the month of March as kind of extremes in a way during the year. There are not much sun here before February, so we looked at March as kind of a winter month. So if we instead look at workplace charging, if you would consider solar energy on non-residential buildings, and then instead of charging at home, as we know that most people do now, we could facilitate charging at the workplace instead. The situation looks much better. And in this case, we have a solar fraction of 78% in July, so that we can charge with 78% solar power in this scenario, and also 32% in March, so that we see that it's also a possibility in the spring and autumn, even up here where we live.
Clara, we have about 2 minutes left in your presentation.
Okay. I also wanted to add a kind of very simplified study that we made of what it would look like on a single household level. And we found that the really easiest way to adjust your solar fraction would be just to orient your solar energy system not towards the south, which would be the optimal if you consider the total amount of energy, but just by orienting it slightly to the west, we could cover much more of the peak in solar energy or in charging. So really the result from this study is that if we look at just the energy demand, we can cover up to 100% uptake of EV charging in Tromsø with solar energy. But that is if we install solar energy on 50% of the suitable area, then we could cover up to 100% EVs during all times of the year. But during summer, even with 10%, we could cover all the EV charging, even in Tromsø. So we see that home charging is not a good fit for solar energy. So if you want to increase the uptake of solar energy and reduce the peaks in our large-scale solar integration, we'll consider looking more at workplace charging. And if you look only at the single household level, orienting solar energy systems to fit your your schedule. But this is, as I said, this is kind of a theoretical study, because we also see that, as was discussed by the previous speaker, I think, experience from Norway now show that even though we have had quite a lot of, or we have had a large uptake of EVs, the grid effects that we feared haven't really occurred. So there hasn't been a lot of breakdown in the grid due to a lot of EV owners charging at the same time in the same street, and basically it's been a problem. It's projected to be possibly a problem in some really a few areas. For example, areas with a lot of holiday cabins where people usually come with empty batteries and all go there at the same time during the holidays. So that is one area, and of course there are quite a lot of these areas in Norway. It's a popular thing to own a holiday cabin, but this is one of the specialized or special areas where we have where there are projections that there might be grid problems. So this was a very quick and not very detailed description of what we have done. So you can find more in these publications, or please feel free to ask me questions or send me an email, and I'll be happy to to chat with you. Yeah, okay. Thank you.
Great, thanks, Clara. I feel like with Zoom, the appearance of the moderator is like the new hook. So thank you for being mindful of time. It was a really interesting study, and it gave me a lot to think about. So thank you, much appreciated. Now we're going to turn our attention to Alaska. Our next presenter is Clay Koplin, and Clay is the CEO of Cordova Electric Cooperative in Cordova, Alaska, where he's worked with a small dynamic team to develop an advanced microgrid system featuring 100% underground distribution lines and fully automated diesel power plant, hydroelectric power plants, and a battery storage system. He's been working with the U.S. State Department and the U.S. Department of Energy to develop unique remote microgrid solutions. And he's also the mayor of Cordova. So busy guy. Clay, thanks for making time. It's always good to have you here, and we look forward to your presentation.
Okay, so this opening screen is what we're trying to protect. And that was Saturday, I went out fishing. Okay, so this is our grid architecture here in Cordova. And probably can't see my pointer, but we have 2 run-of-the-river hydroelectric projects. We have 1 diesel power plant. We have a new battery energy storage system, and we are microgrid. We're not connected to any other electric utility, and we're not connected by road. So to give you an idea, these squares in this middle grid are 1 square mile grids. So our farthest customer business from town center is about 15 miles. So basically a perfect scenario for electric vehicles. And I'll just show you in the upper right-hand corner, you see an intake to our largest run-of-the-river hydro. And it is spilling power at this time. So you see the water going over the dam. And that's actually the scenario we have today, where we have a 3 megawatt load, and we're probably spilling 3 megawatts of excess hydro because we don't have a reservoir to store it in. So this is what our annual energy use looks like from about a year, from 2012. In this green and yellow in the center is excess hydropower that's all going to waste. That black in the spring and winter months is diesel generation. So our challenge is that we don't have any energy storage that we can shift seasonally from summer excess into winter. As our hydros freeze up in the winter, they just don't produce any power. So in our hydro generation scenario, what we used to do is balance our grid by deflecting excess hydropower in response to system loads. So the good news was that allowed us to be 100% hydro. The bad news is that it cost us a lot of renewable energy. So by allowing a grid scale size battery to balance loads, we freed up an extra 700-800 kilowatts of hydro capacity. So that's a scenario we're operating in today, where our battery is balancing system loads. So we've been waiting for electric vehicle to grid technology to evolve basically for the last 15 years, and we're getting a little closer. But to the left here, in terms of grid architecture, you see that you can have a tightly coupled grid where all the resources on your grid are tied together electrically by power lines and communications and are interactive. Or you can have a loosely coupled grid where you can segment your grid into smaller microgrids that can either communicate with each other or not and reconnect from each other or not. And this may be the architecture for grids as we go into the future. So I did a little napkin comparison of what it would have looked like to balance our grid with electric vehicle battery energy storage instead of a large scale grid battery resource. So if you take our battery energy system all-in cost of $2 million, and its capacity of 1 megawatt of peak power output and a megawatt hour storage. This would have been the equivalent of 52 Nissan Leafs at 2020 prices. And at current capacities, those Leafs would have 3.2 megawatt hours of total storage. And we would be able to balance our whole grid with about 16 Nissan Leafs. So that means that we essentially could have given all of our customers free cars, free electricity. They would have had the energy security, perhaps. Are you losing my audio, Julie? Okay, I heard it get light there for a second.
I can hear you, Clay. You're good.
Okay, good. So we could have given our customers free electric vehicles, free electricity, and as long as we could maintain interactivity with their cars and they kept them plugged in a good portion of the time, we could have offered them the energy security of being able to provide stored energy to their own home or to their neighborhood, for example, and keep their car at some minimum level of charge. And this would essentially reduce diesel use on our whole grid, so it would help reduce their neighbors' electric bills, and it makes the energy more portable. So as you drive your electric vehicles around the system, as long as you keep it plugged in most of the time, you can load shift and peak shift and discharge to the grid at certain times of day or in certain portions of the grid and charge on others. And it gives you all kinds of flexibility. So to summarize the impacts of having interactive EVs as your storage element on a grid instead of grid scale storage, we definitely need some technology improvements, communications, controls, interconnectivity, and that speaks a little bit to standardization, and then commercial arrangements around warranties, battery life, so forth. And these aren't trivial problems. Grid impacts for utility can be positive. In fact, they can be a path to high efficiency for the future, particularly on a microgrid. And then the customer benefits, as I showed in the previous slide, can be huge, right up to having free electric vehicles if the electric utility can use it for balancing and use your battery energy storage when they need. And electric vehicles can be a foundational element of our future grid architecture, where maybe we don't have to have such a tightly wires tied grid and can rely a little bit more on energy shifting, portability, and storage to help us develop a more efficient grid architecture into the future. And that was my once over lately.
Great. Thanks, Clay. We will be switching over to Sam Dennis next. Clay, appreciate your presentation and glad you'll be sticking around for questions because I'm sure people have a lot of them. So Sam is the COO of Renewable IPP, which is an Alaska company with a mission to rapidly expand utility scale solar development in Alaska. They've got 1 megawatt solar farm in our service territory, I know. His past includes electrical design of new solar projects as well as the operation of completed projects. He has a BS in geophysical engineering and worked for ARCO BP for 32 years as a geophysicist, engineer, and project manager. And Sam, looking at your screen, it doesn't look like you're here in Alaska right now. So you're somewhere sunnier.
Somewhere with a good solar resource, a better solar resource.
Good for you. And so if you could take us up to about noon, Sam, that would be great as far as time. And then we'll have plenty of time for questions after.
Okay, shouldn't be a problem. Okay, hey, good morning, everybody. So just got about a half a dozen slides here to give the kind of try to pull a lot of what we heard this morning into the Alaska perspective. And it was very gratifying. A couple of the presentations, especially what Graham was talking about, kind of fits exactly. So let me jump in. So EV charging in Alaska. So in Alaska, we charge our electric vehicles at home. And if for no other reason, there is no alternative. And also there's very little need for it. the first question almost I always get is, but can you drive your electric vehicle to Fairbanks? And my response is, when's the last time you drove to Fairbanks? And most people can't remember. So usually 99% of the time, charging at home works just fine. There's no functional reason that home charging can't happen off peak. I think, I can't remember, one of the previous presenters talked about was you need that car charged up by 7 in the morning when you leave for work, and whether it charges from 6 when you get home or from 1 in the morning, you don't care. You just want it charged when you get up in the morning. The final point is here is the EVs use substantial amounts of energy, and that's the point there is it's material. It's not just a little bit. So those are the key points. Okay, next slide.
And as you turn to, oh good. I was just gonna have Clay mute, but he did.
Okay, we all good? Okay, so there was a Norwegian study done by the Norwegian regulator that, about the cost to upgrade the grid for EVs. And what they showed was if you are coincident with peak charging, then there'd be a cost. I think Graham said they did a study that showed it probably wasn't as big of an issue. But the NVE study showed overnight charging, if you could push people to there, it was basically zero. So no cost. So if you can when you push people to overnight charging, grid upgrades are not needed. So that's a key piece to keep in mind. Okay, so for Alaska, with off-peak charging, no additional utility infrastructure. For generation, certainly we've got lots of generation assets, but even for distribution, our utility revenue is based on retail, of course, but for every extra kilowatt hour the utility sells for EV charging, their cost is only the avoided cost of generation. That's about 40%. So the result is, for every additional EV, you basically are reducing the rate for your members, or if you're a investor owned, you're increasing your profit. And the higher that EV penetration rate, the greater the rate reduction. So I just did a what if case. If you look at these numbers, these are for Chugach Electric for, I don't remember, 6 months or a year ago, but the principle is the same for all of our utilities. So my inputs, I said 10% of members buy an EV. Actually, I'll let you can read the assumptions there. You can vary them. And here's the outputs, is basically the EVs are going to use about as much as your house, and that's consistent with what we heard from some of the other presenters. And with 10% of the members with EVs, you could see an overall rate reduction for all members of something in the order of 6% on your power rates. That's pretty significant because typically power rates only go up. So anything that could push power rates down seems like a no-brainer. So here's the conclusions. From what we've heard the last couple of days, EV ownership could substantially increase before any infrastructure upgrades are needed. Okay, so we've got so few EVs that today you could add lots and lots of EVs with no impact. Maybe you try for a voluntary and say, please charge, in the middle of the night. Most people would. In the midterm, as that penetration increases, you might need some modest improvements, and we heard some of those behaviors, that smart charging and time of use rates have a significant impact on behavior. So that's probably all you need. And it's only in that very long term, when you get to very high penetration levels, that you probably are going to have to start doing some grid enhancements. But what we heard was those are probably going to be pretty minor, probably local transformers, distribution. However, my final point there is, and this is my conclusion, the concerns about those long-term impacts, that where we might get someday, is paralyzing action in the near term. I look and say, if we can get a cost reduction for all members, why wouldn't we take that action? And I feel like right now we're paralyzed because we're looking 10 years, 15 years out and saying, oh, we might have some issues. So that's what I had to share. Over to you, Julie.
I'm right here. Sorry. You were 2 minutes early, Sam. Great job. All right. So thank you for that. That's interesting stuff to take a look through. So now we'll be bringing the rest of the panelists up and facilitating a discussion just really among the panelists, and then we'll start taking some specific Q&A from our from the Zoom call. So, you know, as a utility person, one of the things that we're looking at is, you know, it really just starts with demand forecasting for some of this. I mean, Sam, you just had a great point of, hey, we're looking at this, you know, we're looking at problems 10 to 15 years down the road. And we heard both Graham and Clara say, hey, we were expecting these issues, and they're really not. So how can utilities best forecast their EV demand scenarios? Scott, do you want to take a stab at that one first?
Yep, absolutely. Sorry, just taking myself off mute there. Yeah, it's a challenging question. Just we've done some work back in 2017 with doing various penetration levels, but we've also noticed that things have changed in those past few years too. And so it's a little bit of an iterative process where you take a little bit of a read, make those projections, but you kind of have to come back to it fairly regularly just to see where that planning, how those projections have shifted, just because the landscape has just changed so much and will continue to do so. So unfortunately, infrastructure planning on 15, 20-year horizons, a little bit long compared to how the EVs are changing. So it's a difficult question, but just continual adjustment to that plan over time to meet and squeeze in those time frames.
Graham, do you have any perspective about how Green Mountain Power is doing this?
Yeah, so in terms of the demand impact, because we have all the data coming from the chargers, we know what the average connected load per EV is. It's a lot lower than the nameplate capacity of a charger. So level 2 is typically around 6 kW. If you look at the aggregate load divided by the number of chargers connected, we're closer to 1 kW, which means that there's really good diversity among charging from our EV owners. So it's not that every single EV owner is plugging in at the exact same time. Their charging is varied across hours and it's varied across days. And we can overlay that information on top of our volume projections for how many EVs are going to get sold, and then can get a sense of what the aggregate coincident peak demand impact would be. I think we can do that both on a system level and also a circuit level. Fleet Karma, and I know others have looked at sort of the clustering impact. So people living in the same areas buying EVs means that there's more of a congestion issue on the same transformer. But looking at a system-wide impact, just having the sort of coincident peak and connected load would allow you to get a sense of what that load would be.
So have you guys done feeder-specific analysis?
Yeah, so we have, because we have it with our GIS data. You know, we know exactly which feeder each EV charger is put on, and then can run the analyses like what I showed, where we were assuming that there's an EV at every home and the impacts on different transformers and circuits that have more solar. We're able to align consumption with that solar. What does that impact? How can it allow us to build more renewables on certain feeders? And so having the clean data is really helpful.
Great. And so has that impacted how your utility is doing infrastructure planning?
So definitely part of our IRP, sorry, that was a tongue twister, because in Vermont we have a lot of solar and a lot of efficiency programs. The aggregate impact is not driving load growth, and so it's sort of tempering our load reduction and helping to fill some of, potentially fill some of the daytime solar curve if we're able to align that charging to the middle of the day, which I think Clay and Clara hit on. So definitely a part of our overall planning, but it's not causing us to change anything about how we're already looking at the impacts of different technologies, because it does not, the overall impact of EVs does not even make up for the reduction in baseline load coming from efficiency and solar.
Right. Any other comments on that from the team? Sam, you took yourself off.
Yeah, so Graham, I remember right, you said you guys still are, anytime somebody buys an EV, you guys will give them a free smart charger. And you're kind of, it sounds like that's getting ahead of the curve for you guys. So I guess that's a question. Would you highly recommend that to the utilities up here to get ahead of the curve and start doing that?
Sure. So, I mean, I think we pay for, so I guess there was a question in the Q&A before I hit that on, how are we subsidizing these? Because it's not like we can just, give them away and forever. They're paid for as part of a program called Tier 3, which is a carve out of our renewable portfolio standard that allows utilities to incentivize things like heat pumps, electric vehicles, line extensions, all that have a direct fossil fuel reduction. And so it is sort of an incentive mechanism to help customers get these electrification technologies. Those chargers were paid for with that. However, if we just looked at what is the aggregate benefit from managing those chargers, it's about $120 per year. That's purely the savings realized from avoiding those peak hours. And so if a residential charger figure is close to $600, you could pay for that charger only with a 5-year benefit stream of the aggregate reduction in peaks. And that could be enough to get that charger in the customer's home, which I agree that having that happen at the beginning of the process when a customer is just getting an EV is so important, because losing them and having to ask them later on to install something after they might have already installed a non-connected charger, that's a barrier to getting the controlled technology in there, which can help them realize savings because they can sign up for rates that we can talk to the charger and get data, and then also helps us do more localized management as the number of EVs increases.
Great. And Graham, it's interesting that you mentioned that program because I was thinking about how this crossed over with certain policy. What is some experience with this group about how policy has either impacted in a positive or negative way with grid impact of EVs? Thoughts on that? I'm leaving a nice pregnant pause so people can answer, but it doesn't look like there's, aside from Graham's example, that might be where we are. Clay, I know that you've had done some work with the U.S. Department of Energy to help fund some of your innovations. How are you finding that support from either the state or national level compared with your base rates and how you normally calculate rates? How is that all interplaying for you guys?
I would characterize it more as a collaboration. Ooh, it's hard to get that feedback. I think it's more of a collaboration than support. I think the labs and Department of Energy are learning as much from us as we are from them. Kind of to speak a little to demand management, I think as utilities and monopolies, we kind of have a legacy mindset that it's incumbent on us to somehow manage and plan and coordinate all the activity on the grid, but it's not going to be our grid forever. We haven't seen a lot of solar yet. We haven't seen a lot of electric vehicles yet, but they're coming. So we're trying to look out 10 years and work backwards so that we're making the steps and implementing the practices now that will feed into the grid the way it's going to be anyway, really. So if it's highly transactive, interactive grid, and both the loads are a little more flexible, for example, refrigerators and thermal loads kind of cycling a little more strategically than just arbitrarily, in the same way that energy supply is becoming more dynamic and intermittent as it accesses natural resources. You need less and less and less storage in the middle piece. You can build up demand on the customer side by aggregating devices waiting for energy to become available, for example. So if you start parceling your energy storage out to some on the supply side, some in the middle, in the process space, and then some on the customer side, then you can grab the most cost-effective piece of all of them instead of trying to, for example, create enough supply side storage to manage the whole thing. Then if you can distribute and sectionalize and move some of that out to the end of the line, maybe we shouldn't be thinking about building outlines as we have in the past, or building them at all. So I've wandered into lots and lots and lots of complexity into a picture of how complex the national grid is, especially on the regulatory side, and can just say that we're so fortunate that We have a customer-owned utility that owns everything from their toaster clear up to the hydro plants that serve them, with no regulatory barriers, and in our case, no rate barriers in between. We're kind of the Wild West. We can build the grid however we want to. So I don't want to worry about demand, challenges in the future. I want to worry about providing a grid service suite to our customers that they don't have to really think about their behaviors from an earlier question. They can just kind of plug their devices in and let them operate efficiently and not have to really manage it themselves or rely on the utility to manage it. So that's kind of our vision, I guess. And that's very much the space that the Department of Energy is in, because that's where things are heading. So.
Great. Any other comments on that?
I think I might just add, Julie, how it interacts with policy. I think if we ran that analysis on EV coincident peak demand, and it turned out that that was going to drive a huge cost increase, and we'd have to upgrade a whole bunch of substations and feeders. I think there's a realistic case to be made to consider either something like a Fleet Karma device or a smart charger as a non-wire alternative. I know that's a buzzword, but as a kind of utility-owned or utility-managed asset that can help avoid some of these more traditional upgrades. We know the communication rate is high. Yes, you do need Wi-Fi, and internet connection is problematic in Vermont. We don't have great broadband over the whole state, but it doesn't require very high latency to talk to these chargers. We're not doing active management throughout the day. It's more avoiding these very high price periods and when the grid would be stressed. And so I think the more that that sort of thinking comes into the planning dialogue, that, hey, these devices that are distributed and in customers' homes can actually be incredibly valuable to reducing system costs and carrying that load, that I think will be a way to start moving away from some of the more traditional planning that before we had access to technologies like this that could do it.
Great, thanks. Yeah, and as looking at it from a utility, I mean, when we are considering innovative approaches, what to do, I mean, we have a small amount of money to work with, especially at least in our service territory. We have a lot of infrastructure spread over very few members, and so any sort of investment is significant and needs to be weighed. So a question that I have for you all is, how should utilities be prioritizing their dollars around these around EVs? You hear about incentives for whether it's rates, rate incentives, or purchasing EVs for folks, or rebates, chargers, smart meters, all the different options. Where's the best spend for utilities? Scott, do you want to take that one first?
Sure. Yeah, it's a great question. Where's the best spend for utilities? What, there's many different solutions out there. There's many different objectives out there from the utilities, and so it's a balancing act. But I think right now is a good time for utilities to try these different things and find what works, what doesn't. Public infrastructure is definitely important to reduce some range anxiety, depending maybe around corridors. Testing different TOU rates to see the response is really important too. One thing that I think utilities might find challenging is in some of the smart charging. When you're trying to go for active curtailment, if it's a pilot, makes a lot of sense, but trying to scale that into the program or into an actual program is very sort of costly. It doesn't necessarily roll into an ROI positive program. So I think testing price signals, getting some of that public infrastructure out there would be where I would recommend the initial spend. But there's so many entities out there. It would be great to have a place where we're all connected and working off of some sort of standards or something along those lines. But yeah, so price signals and some public infrastructure would be a great place to begin.
Thanks. Clara, do you have any thoughts from Norway of what's worked there? With you guys have some pretty great penetration in similar circumstances to Alaska.
No, I was thinking a bit about in a way, I think it's kind of gone the other way here. I mean, the incentives have been to get people to buy the cars and to get a lot of uptake of EVs. And that itself has, I mean, Norway doesn't have a car industry, but we have had a lot of development in smart charging infrastructure and ideas for how to, for example, in apartment buildings where a lot of people would like to have electric vehicles in the same parking garage, for example. There's been developments in how to balance between all the Teslas in the garage. And I mean, these kind of smart charging has kind of, I guess that's one of the reasons that we haven't seen these grid disasters. This kind of developed, I think, in the other direction, that because we've had a lot of uptake of EVs, this has developed automatically, so to speak. Also, I didn't mention, but I think one issue that has helped is that Norway in the last years, a couple of years, has had this rollout of so-called smart meters, or really meters that electricity meters that run in both directions, and that everyone in Norway now has hourly measurement and hourly pricing, and that is also opened up for these businesses to develop smart charging solutions. So I'm not sure if this is the right approach, but I think that is generally the way that it has worked here.
Great. Graham, anything to add? And then Sam, sorry.
Sam, you go ahead. I'll think on it a little bit.
I just saw a question online that said, could the savings or the additional revenue pay for the smart chargers? And I just did a quick back of the envelope with that case that I ran. The additional profit, I know you guys don't do profit, but profit would be on the order of $900 a year per EV. So I guess it's the utilities just changing the mindset to thinking of, oh, this is additional costs and infrastructure upgrades, to this is pure profit for us. Or in the case of our co-ops, this is
margin, Sam.
Pure rate reduction for our members. So the question be like, how can I get that additional EV on the grid? And I think maybe that'd be my question is, what's the most successful incentives to get the EV on the grid? So. Yeah.
And from our perspective, I really think we've done surveying of customers, and sticker price is still the #1 barrier in Vermont. So we offer a pretty hefty upfront incentive, and then there's a Vermont state incentive that, when overlaid with the federal tax credit, you can get down to some pretty low numbers on overall net cost of an EV. And in Vermont, where our gasoline price compared to electricity price, it's about half right now. It's charging an EV is about the equivalent of paying $1 a gallon for gas. Of course, in recent weeks, this delta has not been as strong as usual, but the operating savings will do the rest. And so I think if customers are able to get the upfront cost down, either in the form of a lease, that they're able to apply those incentives directly to the lease price, so their monthly cost is lower, or just the overall sticker price of the vehicle, it's easier to make that jump once that sticker price delta has been closed. And we know that because battery costs will continue to come down, we'll get there naturally. I think 2024 was the latest estimate I saw, when an EV and an internal combustion engine vehicle will be about the same before any maintenance operating savings are taken into account. But for now, we're very much focused on the sticker price and try to work with manufacturers and dealerships to run promotions where they take our incentive and are able to offer an attractive lease, since I think that's a little bit of a lower barrier for people who've never driven an EV to be able to lease it and know that if it doesn't work, or by the time the technology improves, they'll be able to get a new one in 3 years.
Yeah, I know when we do our polling of members, it's charging infrastructure and the concern with cold weather performance. Those are the kind of the two barriers we hear most about. So yeah, it's been interesting to try to determine as a utility the best way to work with those, and what is our role as a co-op? What do our members want from us, and what role should we play? So Clay, you're laughing over there. Do you have a comment?
Oh, I just think it's ironic that the biggest concern with batteries or electric vehicles connecting to the grid is the load impacts, the dynamic impacts. but it turns out that lithium-ion batteries, that's where they really shine. The least degradation on a lithium-ion is when you do a shallow cycle, a small kilowatt-hour discharge. So for our grid, for example, for us to take a 500 kilowatt load and just carry that load for a minute while our hydro nozzles respond is only an 8 kilowatt-hour demand. So if you think of 1 megawatt hour and all we need is 8 kilowatt hours to balance our entire grid, we can let our batteries degrade 99% and still be able to manage our grid, balance our grid with those batteries. Because we're not using them for energy storage, we're using them for a power shock absorber in our system. So that means we could be recycling all these batteries and putting them in racks at the utilities after they're used in the cars, because in our case, we're getting 90% of our savings by freeing up the renewables out of the system balancing. Only 10% of our anticipated savings is coming from arbitrage, where we're actually charging with 6 cents a kilowatt hour hydro to defer or offset 60 cents a kilowatt hour diesel. So it's just ironic that they're almost a perfect fit for grid balancing. That's why I was smiling.
And Clay, while you have well, now you've unmuted, but while you've got the mic, I want to move into some of our participant questions. One from Rich Weiss is, could a significant number of EVs in Cordova help recover more of the hydro spill in addition to the new BESS? Can you speak to that?
Absolutely. And as you said, Julie, we're always working with limited resources. We only have 1,500 meters on our entire grid, so we have to watch every penny. So when we make a big move like a battery energy storage system, we have to look out 20 years and say, is this going to compete with other things we do to improve our grid? Is it going to complement them? Turns out it's very complementary. And we see that even though it's going to take a few years for electric vehicle to grid technology to truly evolve, we'll be in a position that it's just going to add value to our battery energy storage, because we can distribute that. We can start distributing it out, but we plan on adding more intermittent renewables, wind and solar. So by the time that happens, hopefully we'll be getting into the extra storage resources to help balance them.
Great, thank you. There's a question for Clara. Clara, can you elaborate a bit on the benefit of EVs and PV at the ends of grid distribution network? Do these systems help improve reliability in these areas?
Well, maybe I was a bit not very specific there, but what I meant was that if you have a lot of EVs charging at the end of a weak or unstable grid, it will not be beneficial for the grid. And the same thing with a lot of PV. So our study was more or less to see, can we counteract this two effects by getting a higher solar fraction in the EV charging. It hasn't been a problem in Norway now. I mean, the most, as I don't remember now who referred to this study, that if we can push the charging to nighttime, we will really don't have to spend anything on upgrading the grid due to EVs. So this was more of what can we do to balance two unfortunate effects. So I wasn't very specific there.
Well, and then a follow-up question to that is, there was a few questions around, did you include either smart charging, managed smart charging, or batteries in your analysis, and how that adjusted the results?
We haven't done that at this point. No, I saw this question about whether we could improve the solar fraction with smart charging. One thing that we looked at together with our industry partners was they were managing solar charging points where they actually tried to control the charging based on the solar irradiation, so that if you charge at this charger, you will get a lower voltage or a lower power level if there is less sunshine outside, for example. But when we looked at single residential buildings, it's at least for people who drive to work and charge from at any point when they get home and during the night, it's difficult to utilize more of the sun with smart charging, but we have discussed a lot of residential batteries here. Or I'm really, yeah, it would be really interesting to see further development in vehicle to grid. Yeah.
Graham, follow-up question for you. There was in your graph where you were showing the decrease in load, but then there was a spike at the end of it. How does your system handle that influx?
Yeah, so I think we call that the snapback. And right now we are not doing anything special to manage it. That's really because it's still a very low percentage of total system load. We have the ability to do things like at the end of the event where we're doing the full curtailment, let chargers come back online, but only at 50% or 25% of their max load. And so there are ways to sort of feather the return so that it all doesn't come back and create a big spike in demand at the same instant. And so definitely is something we will be doing as more EVs are adopted. But right now, just because it's still sort of hidden within the overall load that we see on all of our circuits, hasn't risen to the level that it's required yet.
Great. And then Scott, there were some questions for you on how you're pulling your data. And can you speak a little bit more to that?
Yeah, absolutely. So when I mentioned earlier around a connected car device, it's basically a telematics device that clips in the OBD port of a vehicle. And so it's going to read whatever that CAN bus is communicating from the station. But that's the primary way that we collect the data. There has been in certain programs where we've combined and collected data from the station as well, such as like a charge point or a flow station, but it's usually through that C2 device. Where we're moving in the future, we'll be going right to the vehicle via API as we establish more OEM relationships, and Geotab really brings them to the table just because of the size of the company. But Tesla's in that mix, GM, Ford, and so we look to go straight to vehicle in the future, but right now it's through that C2 device.
Great. And there were some questions too around the thresholds of time of use rates. If folks have thoughts on, if you do want to shift your load around, are there certain thresholds, differences, changes for time of use rates that are kind of standard, more effective? Any findings on that? Graham, you're nodding your head. You want to take that?
I've seen, so I know, try to dig up the study, but EVs are way more elastic to price signals than most home loads. I think that's because it is so easy to shift without really needing to do anything. And so typically, you need a strong price difference, like a 2-to-1 ratio, to get customers to do anything. In the case of our program, some customers are allowing us to manage their charger with no monetary compensation, and then even our proposed on and off peak rate, the ratio it's about they're off by about 40%, and so nowhere near doubling. I think if you really want to incentivize daytime use to soak up solar, that would be an opportunity to potentially send real-time signals with prices hourly that are reflecting either our regional rates at the wholesale level or the sort of local availability of excess demand. But I think it's in general, everything I've seen that looks at elasticity of demand and pricing, EVs, you need a much lower delta between the on and off peak rates to incentivize customers to shift.
Great, thanks. That makes sense. Scott, did you have any more to add? You had your mute off, and we'll do this as a kind of our last wrap up because I know it's time to shift over to our closure of the conference.
Yeah, just to I was just in agreement with what Graham was saying. We don't see the need for a huge price signal to get people to shift their charging. And in some cases, as Graham said too, we see that people will change their charging behavior without a price signal, and just being able to get some of their own driving data could be, how they charge, their battery degradation, something like that. Just to be part of a program, they'll shift their load. And I always think of EVs, and I think people, the public, customers are coming around to it, as EVs are, to me, similar to charging your cell phone. I mean, when you charge it overnight, and it doesn't take much behavioral response to get that behavior going and into our routines. So just wanted to agree with what Graham was saying.
Great. And I think, Sam, it's something you predicted in yours too. People will probably be able to do this without it. Well, I really appreciate this group. It was a very diverse group from a diverse areas, and I think we covered a lot of ground. So thanks again for your patience with me initially, and I will turn it back over to Tim for close up.
Thank you so much, Julie, and thank you to all the presenters here for the Grid Impact session. It really is a pleasure to hear the insights, both of the research projects and of the actual utility work that is going on in the session here for Grid Impacts. And that's true, of course, for all the different sessions we've had over this last 2 days. And a quick wrap-up comment for this session for the panelists here. There are a few other questions that were posed in the question and answer box there. If you have the ability and the time, it would be great to have you respond to a few of those additional questions. And that way we can get that as part of the record for this particular conference and get that information out to the various audience and attendees here as well. And that will help us achieve one of the goals here that we've got, which is identifying what information needs, what research opportunities still exist out there, essentially what we don't have answers to at this point. So quick highlight here, in my mind, there is so much work that has been done in the electric vehicle space. As we've heard through the last 2 days, the transportation sector is really moving towards electrification. And there are different ways we can either prepare for that future, or we can potentially incentivize and accelerate when that future comes to today in terms of the availability of electric vehicles and the preparation for the grid for those electric vehicles for charging. And really that strong policy environment, that architecture that's needed at various levels of government and then down to the utility in terms of policies at the utility. We heard policy leadership is really important. That's something that I think was certainly evident in that first session, the policy environment session, and is really echoed throughout many of the other presenters from the other sessions as well. Research here, I think there's been good comment here that there are very good questions that we need to address and making inquiries on, but we shouldn't let that necessarily hold up action on electric vehicles on that policy side. And we should look at the market solutions and allow those to promote electric vehicle use in general. But really around, say, operations and performance on those electric vehicles, the information that we heard today in the operations and performance session regarding our colleagues down in Minnesota, it's great to hear that you all are part of the vanguard testing those electric vehicle buses, those Proterra buses. We have the opportunity to learn from those lessons learned that you're sharing and really hopefully integrate some of those electric vehicles in our communities here. And I know Juneau's doing just that with that particular bus company. And I believe some of the other municipalities are as well, looking at that fleet adoption for public transit. Cold weather research, we certainly have heard that there's a lot of information that comes from various sources, and we have potentially some slightly colder conditions here in Alaska that we need to do some additional research on, and I'm very grateful to Michelle Wilber and my colleagues at ASEP for doing some of that study and planning for additional research. All of the comments through that, through the last 2 days, we heard lots of good anecdotal responses from participants here saying, hey, here's how my electric vehicle does in Fairbanks under these conditions, with certainly some range loss there, but it still means that electric vehicles are working at very cold conditions. And looking again towards the grid impacts, I think there is so much opportunity here, as we just heard in our last session, to really look towards the future, start planning to make sure that we don't have adverse impacts at the various levels of our grid, especially at the distributional level. But as we were hearing our panelists discuss, from the different areas, the different territories and different utilities, at this point, the utilities are saying there probably isn't much that we have to worry about at these lower penetration levels of EVs. And what we need to do is start thinking about those higher penetration levels of EVs and shaping both policy and programs to make sure that we're really maximizing the assets of our electric utility infrastructure. And Clay, I think you were one of the people who said it, certainly not the only, but thinking about that grid of tomorrow, it does seem that there's more and more emphasis on distributed energy resources, electric vehicles being one of these important ones, of course, that we're talking about here today. So lots of great information. I thank all of the presenters here for participating, and I really want to thank the two entities here that are bringing all of this together, and that's Alaska Center for Energy and Power and the U.S. Arctic Research Commission. Without the interest in bringing these topics forward, we wouldn't all be here today. And lastly, I would thank all of you as attendees. We've had incredible representation, about 170 or so people signed up, and lots of folks participating actively in the chat boxes and the question and answer